What if our universe is just one page in an infinite cosmic library? Think about that for a moment. When you look up at the night sky, at all those glittering points of light, you're seeing only the tiniest fraction of our own cosmic neighborhood. Galaxies swirl in vast, silent dances. Stars are born in violent, beautiful nebulae, and planets circle in endless orbits. It's breathtaking, but it might also be just the beginning. That grand, majestic cosmos we call home could be merely one single volume on a shelf that stretches forever into the dark. This is the profound and puzzling mystery of the multiverse. It's a concept that pushes the very boundaries of what we can comprehend, suggesting that everything we know, every person, every star, every moment in history, might be repeating in endless variations across a reality so vast it defies imagination. So how many of these parallel worlds could actually be out there? Is the number finite, or is it truly infinite, an endless sea of possibilities where every choice branches into a new reality? This question isn't just science fiction anymore. It's a serious frontier of modern physics, born from our most powerful theories about how reality works at its most fundamental level. The answers that scientists are uncovering are stranger and more wonderful than any fantasy. We're about to go on a journey together, a journey through the wildest ideas that physics has to offer. We'll explore theories that suggest new universes are being born all the time, bubbling into existence in a never-ending cosmic foam. We'll investigate the possibility that our universe is just one bubble in a vast cosmic landscape, and we'll even confront the haunting idea that an infinite number of versions of you might be living out every possible life right now, in worlds almost identical to our own, and in others so alien we couldn't even begin to picture them. This exploration is more than just a tally of theoretical worlds. It's a quest to understand the very nature of existence itself. It touches on who we are and our place in the grand scheme of things. To stick with this journey is to open your mind to possibilities that can reshape your entire perspective on reality. It's a path that leads through cutting-edge science, mind-bending mathematics, and philosophical wonders, and it all starts with a single, simple, but utterly transformative idea that our universe is not alone. So let's begin this adventure and see just how deep the cosmic rabbit hole goes. Before we can even begin to tally up the number of these cosmic duplicates, we have to get one thing straight. What exactly are we counting? The word multiverse gets thrown around a lot, but it's crucial to understand that it isn't one single, tidy idea. It's more like an umbrella term sheltering a whole family of theories, each with its own unique origin story and set of rules. This isn't about the fantastical parallel worlds you see in movies or comic books, where you might meet a version of yourself with a different hairstyle. We're talking about serious scientific frameworks, hypotheses that have emerged naturally from our most tested and respected laws of physics. These aren't just wild guesses, they are potential consequences of our deepest mathematical understandings of reality, pushing at the very edges of what our equations suggest is possible. The philosophical roots of this concept are ancient. Thinkers have long pondered the existence of other worlds, but the modern scientific multiverse is a different beast entirely. It didn't sprout from pure speculation, but from the thorny, unresolved problems in 20th century physics. When brilliant minds applied the rigorous mathematics of quantum mechanics and cosmic inflation to the beginning of our universe, they found that the solutions their equations pointed toward often implied the existence of more than just our one cosmos. It was a shocking, almost unintended byproduct of the math, so while the idea feels like science fiction, its foundation is built on the same bedrock that gives us GPS satellites and predicts the behavior of subatomic particles. This leads us to a critical distinction. When physicists talk about a multiverse, they could be referring to several fundamentally different structures. One major category involves universes that are truly separate from our own in space and time. perhaps born in their own Big Bang events forever beyond our observational horizon. Another type suggests layers of reality right on top of our own, like ghostly sheets of paper stacked together, where alternate versions of events are unfolding in dimensions we cannot perceive. And yet another concept proposes that every possible outcome of a quantum event literally happens, spawning a continuously branching tree of new universes with every passing moment. Recognizing these different flavors is the first step, because counting the number of multiverses is meaningless unless we specify which kind of multiverse we're discussing. The answer could be a finite but astronomically large number, or it could be a literal, mind-shattering infinity. To truly grasp this first and perhaps most profound type of multiverse, we need to rewind the cosmic clock back to the very first fraction of a second after the Big Bang. Our prevailing theory of the universe's infancy is called cosmic inflation, and it's a concept as radical as it is elegant. Developed in the early 1980s by physicists like Alan Guth, inflation proposes that the newborn universe underwent an unimaginably brief but stupendously fast period of expansion. Think of it like this: in less than a blink of an eye, a region of space far smaller than a single proton was stretched to a size larger than our entire observable universe today. This explosive growth solves several major puzzles in cosmology, like why the universe appears so uniform in all directions. But like any powerful idea, inflation came with a stunning and perhaps unintended consequence. It may never have completely stopped. This is where the multiverse bubbles into existence. The leading models of inflation suggest that the driving force behind this hyper-expansion, a strange kind of energy field called the inflaton field, doesn't simply turn off everywhere at once. Instead, the theory indicates that this field can decay like a ball rolling down a hill, settling into a state of lower energy. When it does this in a particular region of space, that region stops inflating violently and calms down into the kind of stable, steadily expanding universe we live in. This stable region becomes what we call a bubble universe, but here's the crucial part. In the broader background space, the inflationary field doesn't vanish. It continues to ripple and fluctuate, and in other places it continues to inflate at a staggering rate. So, while our bubble universe formed and stopped inflating, the overarching space-time fabric containing it is still expanding exponentially, forever creating new regions where the inflation field can decay, giving birth to new bubble universes in an endless, self-replicating process. The result is a vast and ever-growing cosmic foam of bubble universes, each one isolated from the others by oceans of eternally inflating space. A wonderful analogy is a pot of boiling water on a stovetop. The water represents the eternally inflating background. As it heats up, bubbles form, grow, and rise to the surface. In our cosmic pot, new bubbles are constantly nucleating and forming, each one a self-contained universe with its own local properties. They don't pop, they just drift apart in the rapidly expanding water, forever out of contact with one another. This isn't a one-time event. It's a continuous and likely eternal process of creation, meaning the total number of bubble universes is not just immense but truly infinite. Now, the most breathtaking implication of this inflationary multiverse is what happens inside each of these separate bubbles. The process of the inflaton field settling down, an event we might call the local Big Bang for that bubble, doesn't have a single predetermined outcome. The way the field decays can effectively randomize the fundamental laws of physics within that newborn universe. Think of the inflaton field as a landscape of hills and valleys. The specific valley our universe's field rolled in to determine the properties of our reality, the strength of gravity, the mass of an electron, the number of spatial dimensions. But in another bubble universe, the field might have settled into a completely different valley, resulting in a cosmos where the constants of nature are utterly different. In some bubbles, gravity might be so strong that stars form and burn out in mere millions of years. In others, the nuclear forces might be too weak to ever form atoms, leaving a sea of loose protons and neutrons. Some universes might flash into existence and immediately collapse back on themselves, while others could be so dilute that nothing ever coalesces. Our universe, with its just right balance for complexity and life, could be just one rare but inevitable possibility in an infinite ensemble where every conceivable set of physical laws is realized somewhere. This concept, often called the string theory landscape, suggests that what we call the laws of nature may not be fundamental, eternal decrees, but rather local bylaws unique to our cosmic neighborhood. So we arrive at the truly staggering part. Just how many of these bubble universes could the process of eternal inflation actually produce? The numbers involved are so colossal that they defy our everyday intuition completely. Let's start with a scale we can almost comprehend. Our own observable universe contains an estimated 100 billion galaxies, each with roughly 100 billion stars. That's a number so vast we write it as a 1 followed by 22 zeros. Now consider that every single one of those stars is a sun, many with planets, and each planet is made of countless atoms. The total number of atoms in our entire observable cosmos is roughly a 1 followed by 80 zeros. That number is already unimaginably large, a figure that the human brain simply cannot picture. Yet, in the context of the inflationary multiverse, this number, the sum of all the fundamental particles in everything we can ever see, is utterly insignificant. It's less than a single grain of sand on an endless beach. This is because if inflation is truly eternal, the number of bubble universes isn't just a very, very big number. It is, for all practical and mathematical purposes, infinite. But here's a fascinating nuance that often gets lost. Infinite doesn't always mean the same thing. Mathematicians have known for centuries that there are different sizes or levels of infinity. For example, the set of all whole numbers 1, 2, 3, and so on is infinite. Yet, the set of all decimals between 0 and 1 is also infinite, but it's a vastly larger kind of infinity. The first is a countable infinity, like an endless list. The second is an uncountable infinity, so dense and packed that you could never, even in principle, list all its members. Now apply this to our cosmic foam. The eternally inflating background space is not just endlessly large, it's expanding at an exponential rate, forever generating new bubbles. In such a scenario, the total number of bubbles isn't just an endless list, it becomes an uncountably infinite set. The creation of new universes isn't just continuing, it's accelerating, ensuring that the multiverse grows not just larger, but more densely packed with realities than any list could ever describe. This leads to a truly profound, almost dizzying implication. If the number of bubble universes is infinite, and if the physical constants in each one are randomly determined from a vast landscape of possibilities, then every possible universe that can exist does exist. Not just most of them or a lot of them, but every single one. Somewhere out there in the multiversal foam, there is a bubble where the laws of physics are identical to ours, and a version of you is listening to a version of this video, but perhaps chose a different shirt this morning. There will be bubbles where dinosaurs never went extinct, and others where Earth never formed at all. There will be universes made entirely of dark matter, and others that are just vast, empty voids. The existence of an infinite multiverse doesn't just make our universe feel small. It makes every possible occurrence a certainty. Our particular cosmos, with its specific, life-friendly recipe, becomes one inevitable outcome in a cosmic lottery where every possible ticket is drawn an infinite number of times. The reason we find ourselves in this specific, habitable bubble isn't a miraculous coincidence. It's a simple consequence of the fact that in an infinite ensemble of worlds, we could only ever arise in one that allows for our existence. This idea, known as the anthropic principle, is the only selection bias that applies when you have an infinite number of options. We are here because this is one of the places where being here is possible. But the inflationary multiverse isn't the only contender suggesting a staggering plurality of worlds. To uncover an even more specific and mind-bogglingly vast number, we need to venture into the realm of string theory, a framework that attempts to be the theory of everything by proposing that the fundamental constituents of reality are not point-like particles, but incredibly tiny, vibrating strings. The different vibrational patterns of these strings, the theory suggests, give rise to all the particles and forces we observe. It's an elegant idea, but one that comes with a fascinating and controversial consequence. A prediction for the number of possible universes that is so large it challenges the very meaning of the word possible. This is where we encounter the concept of the string theory landscape. To understand this, picture the fundamental fields that govern our universe not as a single, fixed setting, but as a vast, multi-dimensional cosmic control panel. Imagine a panel with hundreds of dials, each one controlling a different aspect of reality. One for the strength of gravity, another for the mass of the electron, a third for the force that holds atomic nuclei together, and so on. In our universe, all these dials are set to very specific, precise values that allow for complexity, chemistry, and ultimately, life. For a long time, physicists hoped that string theory would provide a unique, elegant solution, a single, preferred setting for all these dials that would perfectly describe our cosmos. But as the theory developed, a shocking realization dawned. There wasn't just one solution. There weren't even a million. The number of stable configurations or vacuum states that the equations of string theory allow is astronomically immense. The figure that emerges is around 10 to the power of 500. Now, let's try to grasp what that number truly means. A 10 with 500 zeros after it is a value so colossally vast that it dwarfs every other large number we've discussed. The number of atoms in our observable universe is 10 to the 80, a 1 with 80 zeros. To get to 10 to the 500, you would need to take every single atom in our universe, and then imagine that each one of those atoms was itself an entire, brand new universe, each containing its own 10 to the 80 atoms. And even after doing that, you would still be nowhere close to 10 to the 500. You'd only be at 10 to the 160. You would have to repeat this process of turning every atom into a full universe several more times over just to approach the sheer scale of the string theory landscape. This number isn't just bigger than the astronomical. It exists in a category all its own, defining a landscape of possible physical realities so extensive that it's effectively limitless for all practical purposes. Each point in this landscape represents a unique, stable way for the extra dimensions proposed by string theory to be curled up and compactified, which in turn determines the values of all the fundamental constants and forces. So every one of these 10 to the 500 possibilities is a complete and self-consistent set of physical laws, a potential universe with its own unique character. In some, the electromagnetic force might be stronger, preventing complex molecules from ever forming. In others, the cosmological constant might be vastly different, causing the universe to collapse in a big crunch or fly apart so rapidly that no structures could ever coalesce. Our universe, with its peculiarly life-friendly dial settings, is just one single tiny point in this nearly infinite landscape of possibilities. This concept provides a powerful, if speculative, explanation for why our universe seems so finely tuned for life. If there is only one universe, the perfect settings of its dials appear to be a miracle of unimaginable luck. But if there are 10 to the 500 different possible universes, all with different dial settings, then it's no longer surprising that at least one of them would have the right conditions for us. We inevitably find ourselves in one of the rare habitable universes because we couldn't exist anywhere else. The string landscape, when combined with the mechanism of eternal inflation, suggests a breathtaking synthesis. Our bubble universe is just one of an infinite number of bubbles, but the variety of physical laws inside those bubbles is not random chaos. Instead, they are drawn from a specific, albeit gigantic, portfolio of 10 to the 500 distinct possibilities. This means that while the number of bubble universes is infinite, the diversity of their fundamental laws, while immense, is ultimately finite, constrained by the mathematical possibilities of string theory. Yet this staggering figure of 10 to the 500 is not just a number pulled from thin air. It represents the possible solutions to the intricate geometry required by string theory. To make sense of this, we need to understand what these solutions actually are. String theory proposes that the fundamental building blocks of reality are not zero-dimensional points, but incredibly tiny, vibrating loops of energy. For the math of string theory to work consistently and produce the familiar particles and forces we see, it requires extra spatial dimensions beyond the three we experience. Think of our everyday reality as a long, thin garden hose. From a distance, it looks like a simple one-dimensional line. But if you look closely, you see its surface is a two-dimensional cylinder curled up into a small circle. String theory suggests that at every point in our three-dimensional space, there are 6 or 7 extra dimensions similarly curled up into a fantastically complex, tiny shape called a Calabi-Yau manifold. The specific way these dimensions are folded and twisted determines how the strings within them vibrate, and those vibrational patterns, in turn, set the values for every fundamental constant of nature: the mass of the quark, the charge of the electron, the strength of gravity. Each distinct, stable way of curling up these extra dimensions corresponds to one unique vacuum state in the landscape, one specific setting for the cosmic control panel that defines a possible universe. Now, the number of ways to fold these multi-dimensional shapes is astronomically large. The mathematics involved is incredibly complex, but the result is this famous 10 to the 500, an estimate for the number of stable configurations that could exist. What this means is that string theory doesn't predict one single universe with our laws. Instead, it predicts a vast portfolio of possible physical realities, each with its own unique set of rules. The vast majority of these possible universes would be utterly sterile and lifeless. In most, the forces might be too weak to form atoms, or too strong to allow for anything but black holes. The cosmological constant, which governs the acceleration of the universe's expansion, might be so large that space-time rips itself apart instantly, or so negative that the universe collapses back on itself in a fraction of a second. Our universe, with its peculiarly balanced and life-permitting parameters, represents just one incredibly specific combination of dial settings among 10 to the 500 possibilities. To appreciate just how special our cosmic address is within this landscape, we can perform a simple thought experiment. Imagine you are a cosmic lottery machine, and your job is to randomly select the settings for all the fundamental constants that make a universe. The odds of you dialing in every single one of them perfectly for life all at once are astronomically small, far smaller than the odds of winning every major lottery on Earth simultaneously for millions of years in a row. In a single universe scenario, this incredible fine-tuning seems like an unbelievable fluke, a miracle that demands an explanation. But within the framework of the string landscape, this fine-tuning finds a natural, if humbling, explanation. If there are 10 to the 500 possible universes, then even the most improbable events become inevitable. It's like dealing a perfectly ordered deck of cards. Shuffle a deck once, and the chance of getting all the cards in perfect numerical and suit order is about 1 in 10 to the 68, a number already larger than the atoms in our universe. If you could shuffle a deck once every second for the entire age of the cosmos, you'd still be fantastically unlikely to ever see that perfect order. But if you had an infinite number of immortal card players, each shuffling decks for all eternity, then that perfectly ordered hand would not only appear, it would appear an infinite number of times. In the same way, our universe, with its seemingly miraculous fine-tuning, is simply one of those rare winning lottery tickets that was bound to be drawn somewhere in the vast cosmic landscape. We don't live in a specially designed universe. We live in one of the exceedingly rare ones that allows for asking the question in the first place. Now we venture into a completely different kind of cosmos, one that doesn't just exist far away in an inflating foam of bubbles, but one that is potentially splitting and multiplying right here, right now, with every single moment that passes. This is the multiverse, born not from cosmic inflation, but from the bizarre and counterintuitive rules of the quantum world. To understand this, we need to leave the vast scales of galaxies behind and zoom into the realm of the impossibly small, to the behavior of atoms and subatomic particles, where the rules of reality seem to play by a different book entirely. At this scale, certainty vanishes, replaced by probability and potential. A particle isn't definitively in one place or another. It exists in a blurry cloud of all possible locations, a state physicists call a superposition. It's only when we observe or measure the particle that this cloud of possibilities seems to collapse into a single, definite outcome. For decades, this was the standard, if unsettling, explanation, known as the Copenhagen interpretation. But in the 1950s, a young physicist named Hugh Everett proposed a radically different idea, one that did away with the concept of collapse entirely. His interpretation, now famously known as the many worlds interpretation, suggests that the superposition never actually collapses. Instead, every possible outcome of a quantum event actually happens, but each one plays out in a newly branched parallel reality. The classic thought experiment used to illustrate the weirdness of quantum mechanics is Schrödinger's cat, and it serves as a perfect gateway into the many worlds view. Imagine a cat is placed in a sealed box with a diabolical device, a radioactive atom, a Geiger counter, and a vial of poison. The atom has a 50-50 chance of decaying within an hour. If it decays, the Geiger counter triggers, the vial is shattered, and the cat dies. If it doesn't decay, the cat lives, according to the traditional Copenhagen view, until someone opens the box to look. The atom exists in a superposition of both decayed and not decayed states. Consequently, the poor cat is also in a superposition, both alive and dead at the same time, a ghostly mixture of possibilities. It's only the act of observation that forces the system to choose one state, a definitely alive or a definitely dead cat. Everett's many worlds interpretation offers a much more straightforward, if far more extravagant, solution. There is no superposition of a half-dead, half-alive cat. Instead, at the moment the quantum event occurs, reality itself splits into two separate, equally real branches. In one branch, the atom decayed, the poison was released, and the cat died. In the other branch, the atom did not decay, and the cat continues to live, purring away, completely unaware of its tragic fate in another world. Both outcomes are real, they just exist in different, non-communicating timelines. This idea transforms our understanding of reality from a single, linear timeline into an ever-branching, tree-like structure of parallel universes. And it's crucial to understand that this branching isn't reserved for special laboratory experiments. It's happening constantly at an unimaginable rate. Every time a single photon hits a reflective surface and has a probability of being reflected or transmitted, the universe may branch. Every time an electron jumps between orbits in an atom, every quantum fluctuation in the vacuum of space, every random event that has a quantum mechanical foundation, each one is a potential fork in the road, a moment where the single timeline of reality diverges into multiple parallel streams. Think of your own life for a moment. Every decision you've ever made, from the monumental to the trivial, was likely influenced by countless quantum events in your brain, the random firing of neurons, the unpredictable decay of a single atom. In the many worlds picture, at every one of those infinitesimal moments, a version of you experienced every single possible outcome. There is a universe where you turned left instead of right on your way to work today. There is a universe where you said yes instead of no to a life-changing opportunity. There is a universe where a single quantum fluctuation allowed a different sperm to fertilize an egg, and an entirely different person was born in your place. The branching is continuous and exponential, creating a truly mind-numbing multiplicity of worlds. This leads us to the question of scale, and the number of worlds in the many words multiverse is, if anything, even more difficult to grasp than the infinite bubbles of inflation. Because here, the multiverse isn't just a collection of distant alien cosmoses. It's a fractal-like splitting of our own immediate reality. If we try to quantify it, the number of parallel universes spawned since the Big Bang isn't just a very large finite number. It is, for all practical purposes, infinite. And this is a different kind of infinity from the one we encountered before. The inflationary multiverse is like an infinite space filled with an infinite number of separate bubbles. The many worlds multiverse is like a single, endlessly dividing thread, where every possible quantum history is actualized. The total number of branches would be an exponential function of the number of quantum events that have occurred in the last 13.8 billion years, a number so colossal that it transcends any meaningful finite description almost immediately after the Big Bang. It suggests that there are not just a few, or a million, or a billion parallel worlds, but an uncountably vast ensemble of them, each one a complete and consistent timeline that branched off from our own at some specific point in history. The philosophical implications of this are staggering and deeply personal. It means that somewhere in the vast tapestry of these parallel realities, every single regret you've ever had is soothed in a world where you made the other choice. Every tragedy that has ever struck has been averted in another branch. Every person you've ever lost is still alive and well in another universe. There are worlds where the Roman Empire never fell, where dinosaurs still roam the earth, and where you are a famous rock star. But it also means there are darker branches, worlds where things went far worse than they have here. This isn't a comforting thought for everyone. It can feel like it diminishes the significance of our own choices and experiences. If every possibility is realized, then what makes this version of my life special? Proponents of the many worlds interpretation would argue that it doesn't diminish our reality at all. It simply places it within a broader context. Your conscious experience is tied to a single path through this immense tree of possibilities. The you reading this sentence is the result of an unbroken chain of specific quantum outcomes, a unique timeline with its own joys and sorrows, its own triumphs and failures. The other versions of you are, in a very real sense, other people now, having their own distinct experiences in their own separate worlds. You are not swapping between them. You are living one specific, valuable thread in an unimaginably rich cosmic tapestry. But if this branching is happening with every quantum event, just how many parallel worlds are we actually talking about? The math behind this is not just large, it's a form of numbers that our brains are fundamentally unequipped to visualize. Think of it this way: a single, simple quantum system, like an atom that can be in one of two states, creates a branch for each possibility. Now, consider that the universe is not made of one atom, but of trillions upon trillions of particles, each undergoing countless quantum interactions every single second. The rate of branching isn't linear, it's exponential. With every passing moment, the total number of parallel timelines doesn't just add together, it multiplies. It's like a virus spreading through a population, but infinitely faster. Each new branch becomes the root for its own set of new branches, and those branches spawn their own in a cascade of reality creation that quickly surpasses any finite number. To put a rough scale on this, some physicists have estimated that the number of distinct branches spawned since the Big Bang could be a number like 10 to the power of 10 to the power of 116. Let's try to unpack what that notation even means. A regular googol is a 1 followed by 100 zeros. That's already more than the number of atoms in the observable universe. A googolplex is a one followed by a googol of zeros, a number so vast you could not write it out even if you converted every atom in the universe into a sheet of paper and a drop of ink. The number of many worlds branches is far, far larger than a googolplex. It's a number that is effectively infinite for any practical purpose. It's not the kind of infinity we associate with an endless line, but rather an infinity of constant, relentless division, where the totality of possible histories is being continuously realized. This leads to a profound philosophical question. Is the number of universes in the many worlds multiverse actually infinite, or just so incomprehensibly large that it might as well be? The distinction here is subtle but important. If the universe is fundamentally discrete at the Planck scale, meaning there is a smallest possible unit of space and time, then there might be a finite, albeit astronomically huge, number of possible quantum states, and therefore a finite number of distinct branches that can form. However, if reality is smooth and continuous, then the number of possible variations is truly, mathematically infinite. Most physicists lean towards the universe being discrete at the tiniest scales, which would suggest the number of branches, while unimaginably large, is ultimately finite. But from a human perspective, a number with more digits than there are particles in the universe is for all intents and purposes an infinity. It means that for any event with a non-zero probability, no matter how tiny, there is almost certainly a branch of the multiverse where it happened. This mathematical reality forces us to confront a deeply personal and almost unsettling question. What does this mean for you? If there are countless branches, then there are countless versions of you, each one the product of a different sequence of quantum accidents. There is a version of you who is a celebrated artist, another who is a reclusive farmer, and another who never existed at all. It's tempting to think of these other versions as potential lives you could have lived, but the many worlds interpretation suggests they are all being lived right now, in full color and detail, by individuals who share your origin but are now distinct. Your conscious awareness isn't jumping between these branches. It is forever locked onto one single, winding path through the tree. The you reading this sentence is the result of one specific, unbroken chain of quantum outcomes. The other versions are, in a real sense, other people. They have your memories up to the point of their branch, but from that moment forward, they accumulate their own unique experiences, their own joys and sorrows, becoming separate individuals. This leads to the poignant realization that in the vastness of the many worlds multiverse, every possible tragedy and every possible triumph is happening to someone who started out as you. It can feel like it cheapens our own experiences, as if our choices don't matter because another version of us made the opposite choice. But a different perspective is that it highlights the incredible uniqueness of your own timeline. Out of all the possible paths your life could have taken, you are experiencing this one. The specific combination of events that led you to this exact moment is a narrative thread as rare and valuable as any in the cosmos. The existence of other branches doesn't make your suffering less real or your happiness less meaningful. It simply places your singular journey within a context of unimaginable grandeur. You are not just a random collection of atoms. You are a specific conscious point of view navigating one thread in an infinite tapestry of what might have been. But beyond the branching timelines of the quantum world and the bubbling cosmic foam of inflation, there exists an even more radical and all-encompassing vision of reality. This is the mathematical multiverse, a concept championed by physicist Max Tegmark and classified as his level Roman 4 multiverse. The central idea here is breathtaking in its simplicity and its scope. Every mathematical structure that is logically consistent exists as a physical reality. In this view, our universe isn't just described by mathematics, it is mathematics. We are living inside a specific, incredibly complex mathematical object, and any other self-consistent mathematical structure is just as real, existing as its own separate universe. To truly grasp this, we need to challenge a fundamental assumption about the nature of reality. We tend to think of the universe as being made of physical stuff, atoms, energy, space-time, and that mathematics is merely a human-invented language, a useful tool for describing that stuff. The mathematical universe hypothesis flips this perspective entirely. It proposes that the physical stuff is a secondary appearance, an emergent phenomenon. The true fundamental reality is the mathematical structure itself. Think of a video game world. What is that world fundamentally? It's not the pixels on your screen or the sounds from your speakers. Those are just representations. The actual reality of the game is the code, the algorithms, and the data structures running on the computer's hardware. In the same way, our cosmos, with all its galaxies, people, and history, might be the physical manifestation of an underlying mathematical structure. If this is true, then it raises a profound question. Why should only one specific mathematical structure, the one that happens to correspond to our physics, be the one that gets to be real? The level Roman 4 multiverse says it isn't. It asserts that all mathematical structures have equal physical existence. This leads to a multiverse of staggering diversity, far beyond what we've encountered so far. The other multiverses we've explored, inflationary bubbles and quantum branches, are still bound by a certain set of rules. They operate within a framework of space, time, and quantum mechanics, even if the constants and outcomes vary. The level Roman 4 multiverse has no such constraints. It contains universes where the very fabric of logic is different from our own. Imagine a cosmos built not on 3 dimensions of space and 1 of time, but on 17 spatial dimensions where gravity operates in an inverse cube relationship instead of inverse square. Consider a reality where the number pi has a different value, or where the Pythagorean theorem simply isn't true. There could be universes that are static, 4-dimensional geometric shapes with no time or change at all. There could be worlds that are nothing but an endless, intricate fractal pattern, or a universe that is simply an empty set. The only requirement for existence in the level Roman 4 multiverse is logical consistency. If a universe can be described without contradiction by a set of mathematical axioms, then it is out there, somewhere in the ultimate ensemble of all that is possible. This immediately prompts the question, is this the largest possible multiverse? In a very real sense, the answer appears to be yes. The level Roman 4 multiverse is the ultimate capstone on the hierarchy of multiverses. Think of it as a cosmic matryoshka doll. Level I would be other regions of our own infinite space with the same physical laws. Level Roman 2 is the inflationary bubble universes where the constants of nature can differ. Level Roman 3 is the many worlds quantum branches which give us all possible outcomes within our specific set of physical laws. Level Roman 4, the mathematical multiverse, contains all of the others within it. Every single bubble universe from eternal inflation is described by a specific mathematical structure. Every single branching quantum timeline is a valid mathematical history. The level Roman 4 multiverse doesn't just include them, it subsumes them while also adding an infinite number of other realities that don't obey our physics or even our logic. It is the set of all sets, the ultimate collection of every conceivable and consistent cosmos. This idea pushes the anthropic principle to its absolute limit. In the level Roman 4 multiverse, we find ourselves in a universe with specific mathematical properties, not because those properties are special or likely, but because they are a necessary condition for our existence. We are self-aware substructures that can only exist within mathematical structures complex enough to contain computation and consciousness. We could not find ourselves in the simple, static universe that is just a perfect sphere, because there is no process there for finding to occur. We are necessarily in one of the rare, complex mathematical structures that allow for the emergence of intelligent observers. This explains the seemingly miraculous fine-tuning of our universe without invoking anything beyond sheer mathematical inevitability. In an ensemble that contains every possible structure, our presence in one that supports us is a trivial tautology. Yet, this grand vision is not without its profound philosophical puzzles. If every mathematical structure is physically real, then what about structures that contain beings who do mathematics and conclude that only their structure is real? They would be just as correct from their perspective as we are from ours. This leads to a kind of radical ontological democracy where no universe is more real than any other. Furthermore, the concept of existence itself becomes blurred. Does a perfectly consistent but utterly simple mathematical object like the number 7 exist in the same way our universe does? Tegmark argues that from a bird's eye perspective outside any single universe, there is no meaningful distinction. The physicality we experience is just a particular viewpoint from within our own specific mathematical structure. This idea forces us to confront the very nature of what it means to be real, suggesting that the ultimate reality is a vast, timeless, and impersonal landscape of mathematical truth, of which our vibrant, evolving cosmos is just one single, beautiful example. So just how many of these mathematical universes could there possibly be? The answer to that question takes us straight into the heart of mathematics itself, into a realm of numbers so vast that even the concept of vast begins to break down. We've already grappled with some colossal figures, like 10 to the power of 500 possible string theory vacua. But the number of mathematical structures in a level 4 multiverse is in an entirely different league. To even begin to count them, we must first understand that mathematics deals with different sizes of infinity, and the jump from one size to the next is a leap of incomprehensible magnitude. Let's start with the simplest kind of infinity, what mathematicians call a countable infinity. Think of the set of all natural numbers, 1, 2, 3, and so on forever. This list is infinite, but we can imagine counting through it one number after another, even if we could never finish. This is a countable infinity. Now consider all the fractions between 0 and 1. You might think there are more of them, but surprisingly, the set of fractions is also countably infinite. You can devise a clever list that includes every single fraction, proving that this infinity is the same size as the infinity of whole numbers. It seems like this should be all there is, but it isn't. The real shock came from mathematician Georg Cantor in the late 19th century when he proved that some infinities are fundamentally larger than others. He showed that the set of all real numbers, that is, all the points on a continuous number line, including every whole number, every fraction, and every weird, never repeating decimal like pi, is uncountably infinite. No matter how clever your list is, you can never list all the real numbers. There will always be numbers you miss. This uncountable infinity, often called the cardinality of the continuum, is so much denser and more packed than a countable infinity that it represents an entirely new class of vastness. Now let's apply this cosmic math to our multiverse. The collection of all possible mathematical structures is not just infinite, it is almost certainly uncountably infinite. Why? Because mathematical structures can be built upon the framework of the real numbers. Consider a universe defined by a specific set of equations. Even a slight, infinitesimal change to a single constant in one of those equations could generate a completely different, logically consistent mathematical structure. Since the real numbers allow for an uncountable infinity of such tiny variations, the number of potential structures explodes into an uncountable realm. This means the level 4 multiverse isn't just an endless list of different worlds. It's a dense, continuous tapestry of realities more numerous than any list could ever capture. The number of mathematical universes isn't just a very big number. It is, in a rigorous mathematical sense, a greater form of infinity than the endless list of whole numbers. This leads us to a profound and deeply puzzling question that philosophers and physicists grapple with. In this vast ocean of mathematical existence, are some structures more real than others? From a purely mathematical standpoint, a simple structure like the rules of basic arithmetic has the same logical validity as the incredibly complex structure that describes our universe with its quantum fields and general relativity. But does that mean they have equal physical reality? One perspective is the radical Platonic view that all mathematical structures exist in a perfect, abstract realm of forms, and our physical reality is just a shadow of one of them. In this view, they are all equally real in a metaphysical sense. However, when we talk about physical reality, the kind we can touch, see, and experience, a distinction might emerge. The key differentiator could be the property of complexity and the ability to support substructure that can contain self-aware observers. Think of it this way. The mathematical structure that defines a perfect, featureless plane is perfectly consistent and real in the level 4 ensemble, but it's a boring universe. Nothing happens there. There are no particles, no forces, no change, and certainly no one to wonder about its existence. In contrast, the mathematical structure that corresponds to our universe is incredibly rich and complex. It has laws that allow for the formation of stars, planets, and ultimately, brains that can perform computations and become self-aware. So, while both structures are mathematically real, only one of them has the property of generating what we would recognize as a physical, experiential world. From our perspective within a complex structure, it feels solid and real. The simpler structures, while existing in the ultimate ensemble, don't have any inside from which to be perceived. So, in a very practical sense, they are not physically real to anyone. Their reality is passive and unmanifest, while ours is active and experienced. This idea helps resolve what might otherwise be an overwhelming ontological headache. We don't need to worry about the reality of a universe that is just the set of all prime numbers, because that structure lacks the necessary complexity to contain conscious observers who could ponder its nature. We necessarily find ourselves in one of the complex structures because we are the kind of entities that can only exist in such a place. This is the ultimate extension of the anthropic principle. We don't inhabit a randomly selected mathematical structure from the uncountably infinite set. We inhabit one from the tiny, peculiar subset of structures that are complex enough to allow for self-aware substructure. So, while the level 4 multiverse contains every possible mathematical form, from the simplest to the most complex, the ones that feel physically real are precisely those with sufficient richness to generate their own internal perception of reality. This doesn't make the other structures less valid, but it does mean they remain barren, beautiful mathematical sculptures in the hall of all possible worlds, forever unobserved and silent. Now let's push the boundaries of reality even further, into a realm of physics so strange it challenges our most basic understanding of space itself. We've explored bubbles, branches, and mathematical structures, but what if our entire three-dimensional cosmos, with all its galaxies, stars, and planets, is nothing more than a magnificent illusion, a holographic projection from a two-dimensional surface at the very edge of the universe? This isn't science fiction. It's a serious theoretical framework known as the holographic principle, and it might just provide one of the most profound connections yet to the concept of the multiverse. The story of the holographic principle begins not with the large-scale cosmos, but with the physics of the very small and the very dense black holes. In the 1970s, physicist Jacob Bekenstein made a startling discovery. He realized that a black hole's entropy, which is a measure of the disorder or information content within a system, is not proportional to its volume, as you might expect, but to the surface area of its event horizon. Think about that for a second. All the information about everything that falls into a black hole, every atom, every person, every book seems to be encoded on the two-dimensional boundary that surrounds it, not within its three-dimensional interior. It's as if the contents of a three-dimensional object were perfectly painted onto its two-dimensional surface. This was a bizarre idea, but it was solidified when Stephen Hawking later showed that black holes emit radiation and slowly evaporate, raising a terrifying question. When a black hole vanishes, what happens to all that information it swallowed? If the information is truly lost, it violates a fundamental tenet of quantum mechanics. The holographic principle emerged as a stunning solution. The information isn't lost because it was never actually inside the black hole in the first place. It was always stored on the surface like a cosmic DVD, and the three-dimensional space we associate with the black hole's interior is just a projection of that data. This radical insight was then scaled up to encompass the entire universe by physicists like Gerard T. Hooft and Leonard Susskind. They proposed that what is true for a black hole might be true for all of reality. Our entire observable universe, with its three spatial dimensions, could be a holographic projection from a two-dimensional surface at the cosmic horizon, the farthest point we can possibly see. In this view, the world we experience, with its depth and solidity, is akin to an incredibly high-resolution 3D movie being displayed on a flat 2D screen. Every event, every particle, every force interaction we perceive is actually happening on this distant foundational boundary. The physics that governs our reality is essentially a shadow of a much simpler, lower-dimensional physics playing out on the edge of space. So, how does this breathtaking idea connect to the multiverse? The link emerges when we consider what else might be encoded on this cosmic boundary. If our universe is a projection from a specific two-dimensional surface with a particular set of data, then it stands to reason that other, different two-dimensional surfaces could encode completely different universes. Each self-contained, lower-dimensional boundary could act as the source code for its own unique three-dimensional reality, a separate holographic universe with its own laws of physics. This provides a potential mechanism for a multiverse that is conceptually distinct from the others we've discussed. Instead of an inflating foam of bubbles or a branching tree of quantum outcomes, the holographic multiverse would be a vast collection of independent cosmic projections, each one flickering into existence from its own foundational screen. This perspective offers a fascinating new way to think about counting distinct cosmic entities. In the holographic framework, what fundamentally defines a universe is not its volume or its physical constants first and foremost, but the information content on its boundary. The size of a holographic universe is limited by the amount of information that can be stored on its two-dimensional surface. This leads to a profound and counterintuitive conclusion. The maximum amount of information, the total number of bits required to describe everything in our three-dimensional cosmos, is finite. It's a number proportional to the area of our cosmic horizon in Planck units. This is a huge number, but it is finite. This means that in a holographic multiverse, while there could be a vast number of distinct universes, each one is ultimately a finite information system. They are not infinite in the way an eternally inflating space is infinite. They are more like a vast but countable library of individual holographic films. This creates a compelling bridge between the holographic principle and the string theory landscape we explored earlier. Each of the 10 to the 500 possible vacuum states in string theory could be realized as a distinct holographic universe, each one projected from its own two-dimensional boundary with a specific data set that defines its unique physical laws. The holographic principle gives these abstract mathematical possibilities a potential physical embodiment. It suggests that the cosmic landscape isn't just a list of potentialities. It could be a directory of actual, functioning holographic projections. The number of such universes would then be tied to the number of stable, distinct lower-dimensional boundaries that can exist, which, while astronomically large, might be finite, offering a potential way to quantify the seemingly unquantifiable vastness of the multiverse. In this view, reality at its most fundamental level becomes a form of information processing. and the multiverse becomes the ultimate ensemble of cosmic programs, each running its own unique simulation of a physical world. But the cosmic landscape of possibilities stretches even further into dimensions we cannot see and structures that defy our everyday intuition. To explore this next layer of the multiverse, we must dive into the depths of one of physics' most ambitious frameworks, M-theory. This is the 11-dimensional successor to string theory, and it gives rise to a concept that reimagines the very fabric of our existence, the brain multiverse. In this vision, our entire universe, with all its galaxies, stars, and planets, might not be a free-floating bubble in an empty void. Instead, it could be a three-dimensional island, a membrane, or brain for short, drifting within a much larger, higher-dimensional space. To grasp this, you need to picture the higher-dimensional arena in which this cosmic drama unfolds. M-theory posits that there are 11 dimensions in total. We are directly aware of the 3 dimensions of space and 1 of time, but the remaining 7 spatial dimensions are curled up into shapes too tiny for us to perceive. Now, within this 11-dimensional reality, there exist objects of various dimensions. Just as a 0-dimensional point, a 1-dimensional string, and a 2-dimensional membrane exist in our world, M-theory allows for higher-dimensional analogs. Our universe in this picture could be a 3-dimensional membrane suspended within a grand, higher-dimensional expanse often called the bulk. Think of it like a single, impossibly thin slice of bread floating in a vast cosmic loaf. All the matter and forces we know, protons, electrons, light, you and me, could be fundamentally stuck to this brain, unable to venture into the full richness of the bulk dimensions. The only force that might freely traverse this higher dimensional space is gravity, which could explain why it is so phenomenally weak compared to the other fundamental forces. Its influence is diluted as it leaks out into the extra dimensions. This setup leads to a breathtaking possibility. Our brain is almost certainly not alone in the bulk. Just as many slices of bread make up a loaf, there could be a vast number of other brains, each one a complete universe with its own particles, forces, and potentially even its own unique laws of physics, all floating parallel to one another in the higher dimensional void. Some of these brains might be mere microscopic distances away from us in an extra dimension we cannot point to or perceive, making them closer than the screen you're looking at, yet forever separated by a fundamental gulf in dimensionality. In this cosmic architecture, the multiverse becomes a vast stack of parallel realities, each one a self-contained cosmic island, largely unaware of its neighbors. The dynamics of this brain world are where things get truly spectacular, offering a potential mechanism for the creation of universes that rivals the drama of the Big Bang itself. Imagine 2 of these parallel brains, these immense cosmic sheets, slowly moving through the bulk. They could oscillate, drawn together by some force across the higher dimensions. Over cosmic timescales, they might eventually collide. The energy of such a collision would be beyond comprehension. When these 2 gargantuan 3-dimensional worlds slam into each other, the impact wouldn't be a destructive crash in the way we think of it. Instead, according to models like the ekpyrotic universe scenario, this collision would release an immense fireball of energy and matter, effectively seeding a new hot, dense state, a brand new beginning for a universe, or perhaps even causing a big bang for the brains involved. The universe we see today, with its uniform expansion and cosmic microwave background, could be the aftermath of just such a primordial collision between 2 brains in the distant past. This leads us to the question of numbers. How many of these parallel brains could be drifting in the higher dimensional bulk? The answer is not pinned down by a single number like the string landscape, but the potential is once again staggering. The number isn't necessarily infinite, but it could be astronomically large. The geometry and stability of the extra dimensions in M-theory could allow for a vast number of distinct brains to coexist. Some estimates, based on the possible configurations of the theory's mathematical framework, suggest numbers that could rival the 10 to the 500 vacua of the string landscape. Each of these brains could have different properties. Some might be identical to ours, hosting parallel versions of Earth and human history. Others could be radically different, with more or fewer dimensions of their own, or with physical constants so alien that matter as we know it could never form. We could be living in a vast, higher-dimensional metropolis of parallel worlds, a cosmic city where each skyscraper is an entire universe, and we are confined to a single floor, completely oblivious to the bustling reality just millimeters away in a direction we cannot move. This concept provides a powerful new perspective on our own place in the cosmos. We are not just inhabitants of a universe, we may be citizens of a single plane in a multidimensional reality of almost unimaginable richness. The brain multiverse doesn't just suggest that other worlds exist far away. It implies they could be right here, all around us, separated by a gap we are fundamentally unequipped to cross. It turns the science fiction trope of parallel dimensions from a fantasy into a serious, mathematically grounded possibility, emerging from our most advanced attempts to unify gravity with quantum mechanics. The search for evidence of these extra dimensions and neighboring brains is an active frontier in physics, with experiments at particle colliders like the Large Hadron Collider looking for clues, such as particles that momentarily escape our brain, or subtle traces of gravitational waves from long ago brain collisions echoing through the very fabric of our cosmos. Now let's take a step beyond the cosmic foam, the quantum branches, and the mathematical ensembles, and consider a possibility that hits closer to home in our technologically accelerating age. What if our universe, for all its majesty and mystery, isn't a naturally occurring cosmos at all, but an artificial construction, an incredibly advanced simulation running on some kind of cosmic computer? This is the simulation hypothesis, a concept that has leapt from philosophy and science fiction into mainstream discourse, championed by thinkers like Nick Bostrom and tech visionaries like Elon Musk. The core argument is both simple and profound. If it is possible for a sufficiently advanced civilization to create a realistic, conscious simulation of a universe, and if such a civilization has any interest in doing so, then over the vast expanse of cosmic time, the number of simulated realities would vastly outnumber the one base physical reality. Statistically speaking, if these conditions hold true, it is almost infinitely more likely that we are living inside one of those countless simulations than in the original ancestral universe. This isn't just a wild guess, it's a logical argument built on a few key premises. First, we must assume that consciousness is not magical, but rather a product of complex information processing. If that's the case, then there's no fundamental reason why a powerful enough computer couldn't host conscious minds. Second, we look at our own technological trajectory. We are already creating increasingly immersive virtual worlds, from detailed video games to rudimentary VR environments. It seems plausible that a civilization thousands or millions of years more advanced than us could achieve simulations indistinguishable from reality for the beings within them. The final step is the statistical one. Imagine that first, original civilization. They might run one simulation, or 1,000,000 or 1,000,000,000. Each of those simulated worlds, if sufficiently advanced, might eventually develop its own civilization that then creates its own nested simulations. The number of simulated realities would quickly explode into an astronomical figure, creating a vast multiverse of virtual worlds, all running within the hardware of higher levels of reality. In this grand tree of existence, the root, the one original universe, would be a singular rarity, while the branches, the simulated descendants, would be virtually countless. So how does this digital multiverse fit into our cosmic tally? It introduces a completely new category of universe that is created not by physical processes like inflation or quantum branching, but by deliberate design and computation. These simulated realities are self-contained systems with their own consistent laws of physics, which are really just the rules of the program. From the inside, they would feel just as real and fundamental as our universe feels to us. The key question is whether they count as genuine universes in the multiverse catalog. From a purely experiential standpoint for the beings inside, the answer seems to be yes. If you are a conscious entity whose entire reality, thoughts, and sensations are generated within a simulation, that simulated world is your universe. Its reality is as valid and meaningful to you as any base-level cosmos. Therefore, if the simulation hypothesis is correct, it would imply the existence of a multiverse so vast it dwarfs even the inflationary foam, a near-infinite stack of virtual worlds, each one a universe unto itself for its inhabitants. This idea forces us to confront deep philosophical questions about the nature of reality and consciousness. If we are in a simulation, then the laws of physics we work so hard to decode are not fundamental truths of nature. They are the source code of the simulation, the algorithms chosen by the programmers. The puzzling fine-tuning of our universe, which we've explored through the lens of the string landscape and the anthropic principle, could have a much simpler explanation. It was designed that way. The programmers may have set the constants of nature to allow for complex structures and life to emerge, either for scientific study, for entertainment, or for reasons we cannot even fathom. This perspective doesn't necessarily diminish our reality. It just recontextualizes it. Our struggles, our joys, our art, and our science are no less meaningful if they are running on a substrate of silicon or some other futuristic computing material instead of fundamental fields. Meaning is derived from experience, not from the underlying hardware. Yet, the simulation hypothesis is not without its fierce critics and major challenges. One of the most common objections is what's often called the simulation stopper. Perhaps it is physically impossible to build a computer powerful enough to simulate an entire universe down to the quantum level. The energy and computational requirements might be prohibitive, even for a type Roman III civilization on the Kardashev scale. However, proponents counter that a perfect atom-for-atom simulation might not be necessary. Our own brains don't perceive the world in perfect, full-resolution detail. A simulation could be rendered in high detail only where and when it is being observed, much like a video game only loads the parts of the world the player is currently exploring. This optimized rendering could drastically reduce the computational load, making the project feasible. Another profound challenge is the question of consciousness itself. We still have no complete scientific theory explaining how subjective experience arises from physical processes. Until we do, we cannot be certain it can be replicated in a digital system. The simulation argument hinges on the assumption that consciousness is substrate independent, that it can run on brains or computers equally well. But this remains an unproven, though widely held, belief in philosophy of mind. When we compare the simulation multiverse to the other types we've discussed, fascinating parallels emerge. It shares a structural similarity with the level Roman IV mathematical multiverse, as both propose that our reality is an instantiation of a set of rules. In one case, the rules are discovered mathematical structures. In the other, they are written code. The simulation hypothesis also creates its own kind of branching multiverse. Every time a simulated civilization reaches a point where it can run its own simulations, it spawns a new level of virtual reality, creating a fractal-like stack of worlds within worlds. This digital hierarchy is a multiverse of a different order, one defined not by physical distance or quantum probability, but by levels of computational abstraction. We could be living in a simulation that is itself running inside another simulation, in a chain that extends upwards for countless layers, with the true base reality forever hidden from our view. Ultimately, whether we consider simulated realities as part of the multiverse depends on our definition of what constitutes a universe. If a universe is a causally connected domain with its own consistent laws and the potential for conscious experience, then simulated worlds clearly qualify. They may be the most common type of universe in the grand scheme of things. The simulation hypothesis doesn't necessarily invalidate the other multiverse theories. In fact, it could encompass them. The programmers in the base reality might be running a simulation whose core physics is based on eternal inflation or the many worlds interpretation, meaning our local multiverse of bubbles or branches could be part of their simulated reality. This adds another dizzying layer of meta-reality to our exploration, suggesting that the different types of multiverses we've catalogued might not be mutually exclusive, but could be nested within one another in a structure of almost incomprehensible complexity. But our journey through the cosmic catalogue of multiverses doesn't end with digital simulations or higher dimensional brains. There is another profound possibility, one that reimagines the entire life cycle of the cosmos. What if the universe has no true beginning or end, but instead is engaged in an eternal, rhythmic dance of death and rebirth? This is the cyclic model, a vision where the cosmos we see is not a one-time event, but merely the latest incarnation in an infinite series of universes, each one born from the ashes of the previous. In this framework, the concept of a multiverse unfolds not across space, but across deep, immeasurable stretches of time. To understand the cyclic model, we first need to challenge our standard story of cosmic origins. The prevailing Big Bang theory paints a picture of a singular beginning, a moment of infinite density from which space and time themselves emerged. For decades, the ultimate fate of the universe seemed to be a choice between two bleak outcomes: either a gradual, cold fade into nothingness as expansion continues forever, or a dramatic reversal leading to a fiery, big crunch where everything collapses back into a point. The cyclic model elegantly ties these two ideas together into a single, grand narrative. It proposes that the universe undergoes an endless sequence of expansions and contractions. Each cycle begins with a Big Bang, expands for trillions of years, and then, instead of fading away, reverses course and contracts down to an extremely hot, dense state, only to bounce into a new Big Bang, starting the process all over again. There is no true singularity, no absolute beginning, just an infinite cosmic heartbeat. The mechanism for this incredible bounce is where modern physics adds its most fascinating details. Early cyclic models struggled with the problem of entropy, the universe's tendency toward disorder. If each cycle simply reset and repeated, entropy would accumulate, making each subsequent cycle longer, messier, and different from the last. How could a universe emerge from a chaotic crunch ready for a clean, new beginning? This is where concepts from string theory and M-theory, specifically the ekpyrotic model, offer a compelling solution. Imagine our three-dimensional brain universe floating in a higher dimensional bulk, as we discussed before. In this cyclic picture, the Big Bang is not a creation from nothing, but the result of a collision between our brain and a parallel brain. The immense energy of this collision heats our universe to a phenomenal temperature, creating the hot, dense state we mistake for an absolute beginning. The universe then expands and cools, forming galaxies and stars just as we see. But instead of expanding forever, the gravitational attraction between the brains eventually pulls them back together. They move apart, stretch, and then draw near once more, setting the stage for the next colossal collision and the next cosmic cycle. This leads to one of the most intriguing implications of the cyclic model, the potential for variation. If the bounce from one cycle to the next is not a perfect, pristine reset, then the fundamental constants of nature might not be perfectly preserved. The precise way the brains collide, or the quantum fluctuations present at the moment of the bounce, could slightly tweak the settings on the cosmic control panel from one cycle to the next. Imagine a universe creation engine with a few dials that have a tiny bit of play in them. Each time the engine runs through its cycle, bang, expansion, crunch, bounce, those dials might jiggle just a little, settling into a slightly different position. One cycle might produce a universe where the strong nuclear force is a fraction of a percent stronger, leading to a cosmos where different elements are stable. Another cycle might have a slightly weaker gravitational constant, resulting in stars that live for vastly longer periods. Over an infinite number of cycles, every conceivable combination of physical constants within a certain range would be realized. This presents a fascinating philosophical puzzle. Does the cyclic model describe a single, evolving universe or a sequential multiverse of distinct cosmic epochs? The answer depends on your perspective. On one hand, you could argue it's one universe, a single, continuous entity that periodically renews itself. The space-time fabric may be continuous from one cycle to the next, even through the bounce, meaning there is an unbroken physical connection linking all incarnations. From this viewpoint, it's like a single organism, like a forest that burns to the ground only to regrow again. It's the same forest, just in a new phase of its life. However, if the physical laws and constants change fundamentally between cycles, the case for calling each cycle a separate universe becomes much stronger. A cosmos where gravity is too weak to form galaxies has so little in common with our own that it qualifies as a genuinely different reality. In this light, the cyclic model describes a multiverse strung along the thread of time, a linear sequence of distinct universes, each one causally disconnected from the next by the violent reset of the bounce. We are not living in a universe alongside others, but after an infinite number of others, and before an infinite number more. Now, we approach what might be the most intimate and startling gateway to the multiverse, a concept that suggests new realities are being born not in some distant, inflating void, but right here in the darkest hearts of our own cosmos. We're venturing into the idea that every black hole could be a cosmic womb, a seed for an entirely new universe. This theory, sometimes called black hole cosmology, proposes a breathtaking lineage that our own universe might have been born from a black hole in a parent cosmos, and that every black hole we see might be giving birth to a new cosmos of its own. To understand how this could be possible, we need to peer into the final moments of matter falling into a black hole. According to our best understanding of general relativity, anything that crosses the event horizon is irrevocably pulled toward the center, the singularity. This is a point of infinite density where the known laws of physics break down completely. Space and time, as we understand them, cease to exist. For decades, this was seen as the ultimate dead end, a one-way street to destruction. But some physicists, most notably Lee Smolin, have proposed a radical alternative. What if the singularity isn't an end, but a transformation? The conditions at a singularity, effectively infinite energy and density packed into an infinitesimal point, bear a striking mathematical resemblance to the conditions at the very beginning of our own universe in the Big Bang. This profound similarity suggests a revolutionary possibility. The collapse of a massive star into a black hole might not be a final act of destruction, but a cosmic reset button. The immense gravitational crunch could rebound, triggering a new outward expansion, a new Big Bang on the other side of the singularity, birthing a new space-time continuum entirely separate from our own. This idea elegantly sidesteps the troubling concept of a true singularity. Instead of matter being crushed into an infinitely dense point of nothingness, the physics of the bounce, potentially governed by quantum gravity effects we don't yet fully understand, would prevent the infinite collapse and create a new, expanding universe. In this view, a black hole is not a pit but a tunnel. Its singularity is not a wall but a bridge. The event horizon acts as a one-way membrane, not just for matter, but for causality itself, ensuring that the new universe evolves with its own independent timeline and laws, completely disconnected from its parent. So, just how many of these cosmic generators are at work in our own universe? The number is staggering. We now know that supermassive black holes, with masses millions or even billions of times that of our Sun, lurk at the centers of nearly every galaxy, including our own Milky Way. But these galactic behemoths are just the tip of the iceberg. Throughout every galaxy, there are countless stellar mass black holes, the remnants of massive stars that have ended their lives in supernova explosions. Current estimates suggest there could be as many as 100 million stellar mass black holes in our galaxy alone. And when you consider that the observable universe contains perhaps 2 trillion galaxies, the total population of black holes becomes a number so vast it defies human comprehension, easily reaching into the sextillions, a 1 followed by 21 zeros. And that's just counting the ones we can infer from their gravitational influence. There could be many, many more primordial black holes formed in the early universe that remain undetected. If the black hole cosmology theory is correct, then this number takes on a universe-shattering significance. Each one of those sextillions of black holes could be a universe factory, each one giving rise to its own self-contained cosmos. This creates a multiverse of a different architecture altogether. Not a foam of bubbles or a stack of brains, but a vast, branching cosmic tree. Our universe would be one branch, containing within it the seeds for countless daughter universes. And each of those daughters would, in turn, contain their own black holes, spawning granddaughters, and so on, creating a fractal-like structure of reality that extends forever both upward to our own parent and downward into an infinite future of cosmic generations. This leads to a fascinating evolutionary perspective on the multiverse, one that introduces a form of cosmic natural selection. Think about the properties of a daughter universe. They aren't necessarily identical copies of their parent. The specific conditions of the bounce, the precise way the quantum gravity effects play out at the moment of the new Big Bang, could slightly alter the fundamental constants of physics in the new cosmos. Some daughter universes might be stillborn, with constants that prevent the formation of atoms or stars. Others might be long-lived and fertile, with physical laws that readily produce black holes. Those fertile universes would, by their very nature, produce more offspring, passing on their fruitful physical parameters to the next generation. Over countless cosmic generations, this process would naturally select for universes that are exceptionally good at making black holes. This provides a potential, non-miraculous explanation for why our own universe seems so finely tuned for the existence of these objects. It's not that the universe was designed for life. It may have been shaped by a cosmic evolutionary pressure to maximize the production of black holes, and we, along with the stars and galaxies that are the necessary precursors to black holes, are simply along for the ride. In this breathtaking vision, black holes are not agents of death, but the very engines of cosmic reproduction, ensuring the prolific continuation of reality itself across an infinite family tree of spacetime. Given this incredible array of possibilities, from bubbling cosmic foam to branching quantum worlds, a critical question naturally arises. If all these multiverses are real, why can't we see them? This is the fundamental challenge at the heart of modern cosmology, the search for observational evidence. The scientific method is built on the principle of testability, of making predictions that can be verified or falsified by experiment. So, where is the proof for these other realities? The sobering truth is that by their very definition, most multiverse theories place these other worlds permanently beyond our direct observational reach. Think of it like being in a vast, dark ocean. Our universe is a single ship, its powerful lights illuminating only the immediate water around it. We can see for a great distance, but that distance is finite, bounded by a horizon. Beyond that horizon, the light from other ships, other universes, has not had time to reach us since the beginning of our voyage, and because the ocean itself is expanding, it may never will. This is our cosmological horizon, and it represents the absolute limit of what we can ever see. Yet, scientists are a clever and persistent bunch. If we can't see the other ships directly, perhaps we can look for their wake, for subtle ripples or imprints they might have left on our own cosmic environment. One of the most promising places to look for such fingerprints is in the oldest light in the universe, the cosmic microwave background, or CMB. This is the remnant glow from the Big Bang, a snapshot of the universe when it was just 380,000 years old, cooling from an opaque plasma into a transparent gas. This faint microwave radiation fills all of space, and it is exquisitely uniform in every direction. But it's not perfectly uniform. There are tiny, minuscule fluctuations in its temperature, variations of just 1 part in 100,000. These fluctuations are the seeds that eventually grew into all the galaxies and clusters we see today. For cosmologists, this CMB map is a treasure trove of information about the universe's infancy, and some theories suggest it might also contain clues of a collision with another universe. Imagine for a moment that during the period of early inflation, our bubble universe was forming very close to another one in the eternally inflating foam. As both bubbles expanded at nearly the speed of light, their boundaries could have briefly brushed against each other before being forever separated by the runaway expansion of space. Such a collision would have sent a shockwave rippling through the fabric of our newborn cosmos, a disturbance that would have left a distinct asymmetric pattern in the CMB. It would be a kind of cosmic bruise, a telltale sign of an encounter with a foreign reality. Researchers have meticulously scoured the data from satellites like Planck, searching for specific statistical anomalies or strange, circular patterns in the temperature map that could be explained by such a bubble collision. While a few intriguing, unexplained features have been found, none have yet risen to the level of definitive proof. They remain tantalizing hints, whispers from the other side of the horizon that demand further investigation and more precise future measurements. Another potential source of evidence comes from the ghostly vibrations of spacetime itself, gravitational waves. These ripples, first detected directly in 2015, are generated by the most violent events in the cosmos, like the merging of black holes. But there is also a predicted background of primordial gravitational waves created in the first frantic moments of inflation. The specific pattern and polarization of these waves could, in theory, tell us a great deal about the physics of that inflationary period. Some models of the multiverse make specific predictions about this gravitational wave background. For instance, if our universe is the result of a collision between two brains in a higher dimensional bulk, as in the ekpyrotic cyclic model, the signature of that collision would be imprinted in the spectrum of these primordial waves. It would be a very different pattern from the one predicted by standard inflationary models. Future space-based gravitational wave observatories, like the proposed European Laser Interferometer Space Antenna, or LISA, are being designed with the sensitivity to listen for these ancient cosmic echoes, potentially allowing us to distinguish between different multiverse-generating mechanisms. On the quantum front, the search is even more subtle and conceptual. If the many worlds interpretation is correct and reality is constantly branching, could we ever detect the faint influence of a nearby branch? The standard view is no, because the branches are completely decoherent, they don't interact. But some physicists have proposed incredibly delicate experiments to test the limits of this. One idea involves looking for tiny, residual correlations in systems that are on the verge of triggering a quantum measurement. The thought is that if a branching event has just occurred, there might be a vanishingly small, fleeting connection to the other branch that could, in principle, be measured as an anomaly in quantum interference patterns. These experiments push the very limits of our technological ability to isolate and control quantum systems, and any positive result would be revolutionary, providing the first direct laboratory-based evidence for a parallel reality. So far, no such evidence has been found, but the very fact that we can design experiments to test the idea shows how far this field has moved from pure philosophy into the realm of empirical science. The reason this search is so monumentally difficult boils down to a few fundamental principles of physics. The first is causality. For us to observe something, information from that object must travel to us, typically at the speed of light. But if another universe is truly separate from ours, either outside our cosmological horizon or in a different quantum branch, then by definition no signal, no particle, no form of information can cross from that reality into ours. They are causally disconnected. It's like being in a room with soundproof walls. You can shout all you want, but you'll never hear the person in the next room, and they will never hear you. The second challenge is the nature of scientific proof itself. Science often advances by making a prediction that is later verified. But how do you make a testable prediction about something that is, in principle, unobservable? Proponents of the multiverse argue that we are not testing for the other universes directly, but for the consequences of the theories that predict them. If cosmic inflation is correct and all our other observations continue to support it, then the existence of an eternal, multiverse-generating inflation becomes a natural, almost inevitable consequence. The evidence for the multiverse in this view would be the overwhelming success of the theories that require it. This leads to a fascinating and sometimes heated debate within the physics community about the very definition of science. Critics argue that a theory that predicts a near-infinite number of unobservable universes is not science but metaphysics. It can explain anything because for any strange observation you can always say, well, it's just that way in our particular bubble. This makes the theory, in their view, unfalsifiable, the ultimate scientific sin. How could you ever prove it wrong? Supporters counter that the multiverse is a prediction, not an assumption. We didn't start with the idea of a multiverse. We started with the theories of inflation and quantum mechanics, and the multiverse emerged from the math as a surprising outcome. They argue that as we gather more precise data about our own universe from the CMB, from gravitational waves, from particle accelerators, we are indirectly testing the frameworks that give rise to the multiverse. If those frameworks continue to be validated, the case for a multiverse grows stronger, even if we can never take a picture of it. It's a circumstantial case, built on the preponderance of evidence from our own cosmic backyard, suggesting that the simplest and most elegant explanations for what we see here inevitably lead to a reality far grander than we ever imagined. And so we arrive at a central, almost haunting question that threads through all these multiverse theories. If our universe is so incredibly, delicately fine-tuned for life, does that point to a divine creator, or does it point to a cosmos where every possible ticket gets drawn? This is where a powerful and sometimes controversial line of reasoning comes into play, known as the anthropic principle. At its heart, it's a simple, almost self-evident idea. We, as conscious observers, can only find ourselves in a universe that has the right conditions to allow for our existence. It's a statement about selection bias. You wouldn't be surprised to find yourself living on a planet that has air you can breathe and water you can drink, rather than on a barren, airless rock orbiting a dying star. The fact that you're there to be surprised at all is only possible on the planet that can support you. Now scale that thought up to the entire cosmos. The fundamental constants of nature appear to be balanced on a razor's edge. Imagine you're adjusting the cosmic control panel we talked about earlier. If the force of gravity were even slightly stronger, the universe would have collapsed back on itself in a big crunch shortly after the Big Bang. If it was slightly weaker, matter would never have clumped together to form stars and galaxies. If the strong nuclear force which binds atomic nuclei together were just a few % different, hydrogen would be the only element in existence, and the complex chemistry required for life would be impossible. The list of these cosmic coincidences is long and profoundly precise. The probability of all these dials being set to their exact, life-permitting values by random chance seems astronomically, incomprehensibly small. It's like throwing a deck of cards into the air and having it come down as a perfectly built house of cards. This apparent fine-tuning has puzzled scientists and philosophers for decades, and it demands an explanation. The multiverse offers a powerful and naturalistic solution to this puzzle. If our universe is just one among a vast, perhaps infinite, number of universes, each with its own random set of physical constants, then it's no longer surprising that one of them turned out to be just right for us. We shouldn't be amazed that we won the cosmic lottery. We should expect to find ourselves in one of the very few universes where winning was even possible. In an infinite cosmic landscape, even the most improbable events are not just possible, they are inevitable. There will be universes where the constants are set for a fleeting, sterile existence, and there will be universes where they allow for galaxies, stars, planets, and life. We, by our very nature as observers, are logically bound to inhabit one of the latter. The anthropic principle, when coupled with the multiverse, transforms a seeming miracle into a statistical certainty. This line of thinking, however, walks a delicate line between profound science and deep philosophy, and it has sparked intense debate. Critics argue that using the anthropic principle to explain fine-tuning is a cop-out, a textbook example of a non-falsifiable argument. After all, they say, you can always invoke the anthropic principle to explain anything. The universe is the way it is because if it weren't, we wouldn't be here to see it. It can feel like a circular, almost vacuous piece of reasoning that halts further scientific inquiry. If we accept it too readily, does it mean we stop looking for a deeper, more fundamental theory that might actually predict why our constants have the values they do? Proponents counter that the anthropic principle isn't a replacement for physics. It's a necessary framework for interpreting the physics we have. When our most promising theories, like eternal inflation or string theory, naturally predict a vast landscape of possibilities, the anthropic principle becomes the essential tool for understanding our place within that landscape. It's not that we've stopped looking for a deeper theory. It's that the deeper theory we've found seems to point toward a multiverse, and the anthropic principle is the logical consequence. To truly appreciate the power and the limitations of this reasoning, consider a more grounded analogy. Imagine a vast, endless forest filled with an infinite variety of trees. Most of the trees are twisted, stunted, or barren, but a very, very small number of them, by pure chance, grow tall and strong with lush canopies and deep roots. Now imagine a small bird that can only nest in this specific type of tall, strong tree. That bird will never find itself wondering why it lives in such a perfect tree. It will only ever wake up in one of the few trees that can support its existence. The bird's perspective is limited to the habitable trees. It has no access to the vast, infertile forest that surrounds it. In this analogy, we are the bird. Our observable universe is the single, perfect tree we find ourselves in. The multiverse is the infinite, mostly barren forest. The anthropic principle is simply the recognition of our own inevitable bias. We were always going to be in a place that could support us, so we shouldn't use our own existence as proof that the entire forest was designed for us. This perspective can feel both humbling and liberating. It suggests that the universe wasn't made for us. We are a beautiful but ultimately incidental product of a much vaster and more impersonal cosmic process. Our existence is not the central goal of creation, but rather a rare and precious fluke in an ensemble where all possible outcomes are realized. This doesn't make our lives any less meaningful. If anything, it makes our specific, fragile corner of reality all the more remarkable. We are the universe becomes self-aware, peering out from one of its few fertile islands and trying to comprehend the silent immensity of the whole. The anthropic principle, then, is not an answer in itself, but a guidepost. It tells us that the question, why is the universe so perfectly tuned for life, might be the wrong question altogether. The right question, in light of the multiverse, may be, What are the fundamental physical processes that generate such an immense variety of universes that a few like ours are bound to appear? It shifts the mystery from the specific details of our local reality to the awe-inspiring generative powers of reality as a whole. This notion of endless parallel selves and branching realities forces us to confront some of the most ancient and profound questions of philosophy. If there is a version of you who became an astronaut and another who never left their hometown, which one is the real you? The concept of personal identity, the sense of a continuous and unique self that persists through time, begins to fray at the edges when stretched across the multiverse. Are these other versions truly you, or are they simply individuals who share your origin story up to a certain point, like identical twins who are separated at the quantum level and then live entirely different lives? Your identity isn't just the sum of your memories, it's the specific, unbroken chain of experiences that has shaped your perspective. The you listening to this sentence is the product of a single, winding path through the immense tree of possibilities. Those other selves, while they started from the same seed, have grown into different trees altogether, with their own unique rings marking years of different joys, sorrows, and choices. Your consciousness is tethered to this one thread of reality, and in that sense you remain a singular being, even as your cosmic echoes live out their own stories elsewhere. This directly challenges our most deeply held intuition about free will. We feel in our bones that we are the authors of our own lives, that our choices matter and carve out a unique future from a sea of possibilities. But if the many worlds interpretation is correct, a startling alternative emerges. Every possible choice is made. The feeling of making a difficult decision, weighing the options, feeling the tension, and finally committing to a path might not be a process of selecting one future and discarding the rest. It could be the moment your conscious awareness becomes locked onto one branch of a reality that has already split to accommodate all outcomes. In this view, free will isn't the freedom to choose the future, but rather the freedom to experience a future. You are not a puppeteer pulling the strings of destiny. You are a passenger on a train that switches tracks at every quantum junction, and your conscious experience is the ride along one specific, predetermined route. This doesn't make your life any less meaningful, but it does reframe the nature of choice from an act of creation to an act of navigation through a landscape of already existing realities. Throughout history, long before physicists ever wrote an equation, human cultures and religions have been grappling with these very same ideas about multiplicity and the self. The Hindu concept of Brahman, the ultimate singular reality, manifests in our illusory world of separate forms and identities known as Maya. In this view, the sense of a single, isolated self is an illusion, and the countless individual lives we see are all expressions of the one fundamental consciousness. This bears a fascinating, though not exact, resemblance to the idea that our separate identities in different quantum branches are all part of a single, underlying quantum wave function. Similarly, the Buddhist doctrine of anatta, or non-self, teaches that what we perceive as a permanent, unchanging identity is actually a temporary constellation of ever-shifting elements, a flowing river of thoughts, sensations, and memories with no solid captain at the helm. This resonates powerfully with the notion that you are not a fixed entity, but a specific pattern of information, a story that is being told along one thread of a vast cosmic narrative. Your existence is a process, not a static thing, and in the multiverse, that same process is unfolding in countless other ways. We can find echoes of the multiverse in ancient mythology as well. The Norse envisioned Yggdrasil, the world tree, whose branches held the 9 distinct realms, each with its own laws and inhabitants, from the world of gods to the world of mortals. Aboriginal Australian Dreamtime stories describe a timeless, parallel dimension that interacts with and influences the physical world. And even in the many worlds interpretation of quantum mechanics proposed by Hugh Everett, we see a stark contrast with the dominant Western religious tradition, which often posits a single, divinely created cosmos with a linear history from Genesis to Apocalypse. The multiverse presents a vision of reality that is inherently pluralistic, decentralized, and without a single center or a definitive end. It suggests a cosmos that is less like a carefully composed symphony and more like a boundless, chaotic jazz improvisation where every possible melody is being played at once. So, what is the ultimate meaning of your life in such a vast and crowded cosmos? It's tempting to feel small, to think that your struggles and triumphs are rendered insignificant because they are happening in infinite variations elsewhere. But this perspective misses a crucial point. The existence of other possibilities does not diminish the concrete reality of your own experience. The love you feel for your family, the pain of a loss, the joy of a hard-won achievement, these are not abstract statistical events. They are the very substance of your consciousness, and they are happening here in this universe to you. The multiverse doesn't steal meaning, it recontextualizes it. Your life is not a random, solitary accident in an empty void. It is a unique and precious thread in the grandest tapestry imaginable. The choices you make still matter immensely because they define the character of the specific reality you are weaving. You are living out one of the most incredible stories the cosmos has to tell, and the fact that other stories are also being told doesn't make yours any less beautiful, valid, or worthy of being lived to its absolute fullest. With all these extraordinary possibilities laid out before us, from infinite bubbles to branching quantum worlds, it becomes essential to impose some order on this cosmic chaos. How do we even begin to catalogue such a bewildering array of realities? Fortunately, some of the brightest minds in physics have devised classification systems to map this vast territory, creating a kind of periodic table for parallel universes. Perhaps the most famous of these frameworks comes from cosmologist Max Tegmark, who organized the multiverse into 4 distinct levels, each one broader and more mind-bending than the last. His system provides a beautiful, hierarchical way to understand how these different ideas nest inside one another, like a set of Russian dolls that grow progressively more abstract. Tegmark's Level 1 multiverse is surprisingly simple and is almost a direct consequence of the universe being infinite in size. If space stretches on forever and matter is distributed more or less evenly, then every possible configuration of particles must repeat somewhere. This means that far, far beyond our cosmic horizon, there are regions of space identical to our own where a perfect copy of you is going about their day. There will be volumes where everything is the same except the wallpaper is a different color, and others where Earth never formed. It's a multiverse of sheer spatial repetition, born from the simple logic of infinity. Level 2 is where things get more exotic. This is the realm of the inflationary bubble universes we explored earlier. Here, the different universes aren't just far away in our space, they are separate cosmic domains, each with their own Big Bang and, crucially, their own potentially different laws of physics. This is the landscape of the string theory vacua, where each bubble can have its own unique settings for gravity, particle masses, and even the number of dimensions. Level 2 doesn't just give you copies of yourself, it gives you realms where the very concept of you is physically impossible. Then we arrive at Level 3, which is Hugh Everett's many worlds interpretation of quantum mechanics. In this view, the multiverse isn't out there in space, but is constantly splitting off right here, with every quantum decision creating a new, equally real branch of reality. While it might seem that Level 3 produces the same kind of copies as Level 1, there's a profound difference. In Level 1, your doubles are far away in space, but they share the same history and the same fundamental laws. In Level 3, your other selves branched off at specific moments in the past, meaning their histories diverge from your own. One might live in a world where the Roman Empire never fell, a possibility that wouldn't exist in a Level 1 universe with the same initial conditions as ours. Finally, level 4 is the ultimate ensemble, the mathematical multiverse. This is the idea that every mathematically consistent structure exists as a physical reality. It contains all the universes from the first 3 levels, but it also includes realities that operate on completely different kinds of mathematics, with different dimensions, different logics, and no connection to our physics whatsoever. It is the ultimate capstone, suggesting that our cosmos is just one particular mathematical structure that has the property of feeling physically real to the self-aware patterns within it. Tegmark's system is elegant for its hierarchy, but other physicists have proposed different, more granular ways to slice the cosmic pie. Brian Greene, for instance, in his book, The Hidden Reality, outlines 9 distinct types of multiverses, offering a more detailed taxonomy. His list encompasses many of the same ideas but breaks them down further based on their underlying mechanisms. He separates the quilted multiverse of level 1 from the inflationary multiverse of level 2. He then adds specific categories for the brain multiverse from string theory, where our universe is a 3-dimensional membrane floating in a higher dimensional bulk, and the cyclic multiverse, where universes are born from collisions between these brains in an endless cycle of cosmic death and rebirth. He also includes the landscape multiverse from string theory's vast number of possible vacuum states, the quantum multiverse of many worlds, the holographic multiverse where our reality is a projection from a distant 2-dimensional surface, the simulated multiverse where advanced beings run cosmic software, and finally, the ultimate multiverse, which aligns with Tegmark's level 4. Where all possible mathematical structures are real, comparing these 2 systems reveals the different priorities of their creators. Tegmark's 4 levels are about scope and abstraction, building from the familiar to the utterly alien. Greene's 9 types are more about the physical or theoretical mechanisms that generate the multiplicity. His classification is like a botanist categorizing plants by their method of reproduction, while Tegmark's is like ordering them by their overall size and complexity. This is where the estimates for the number of universes can diverge dramatically depending on which category we're talking about. In Greene's, quilted, or Tegmark's level 1 multiverse, the number of universes is straightforwardly infinite, a consequence of endless space. In the inflationary or landscape multiverses, the number of distinct bubble types might be finite, like the 10 to the 500 of the string landscape, but the number of actual bubbles, if inflation is eternal, is infinite. The quantum multiverse presents a different challenge. The number of branches is not just infinite, but the rate of branching is so frantic that the total number becomes a number of an entirely different, indescribable magnitude. These divergent estimates aren't a sign that the science is flawed. They reflect the fact that we are dealing with fundamentally different kinds of multiplicity. Counting the number of parallel Earths in a level 1 multiverse is a different mathematical problem from counting the number of distinct vacuum states in the string landscape, which is different again from quantifying the branching rate of the quantum wave function. The why behind these divergences comes down to the foundational principles of each theory. An infinite universe gives you infinite copies. Eternal inflation gives you an infinite number of bubbles drawn from a potentially finite landscape of possibilities. Quantum mechanics in the many worlds interpretation gives you a continuous, exponential splitting of reality itself. And the mathematical multiverse posits an uncountably infinite collection of all logically consistent structures. The classification systems help us see that the question, how many multiverses are there, is in fact a bundle of different questions. The answer isn't a single number, but a spectrum of answers, each one tied to a specific vision of how reality is structured at its most fundamental level. Yet for all its power, the concept of infinity brings with it a host of profound puzzles that push at the very boundaries of what science can describe. When we say the number of universes is infinite, have we actually provided a satisfying answer, or have we simply used a mathematical placeholder for a quantity that fundamentally eludes our comprehension? This forces us to confront the limits of infinity itself, not just as a number, but as a meaningful physical concept. In our everyday lives, we deal with finite things. We count objects, measure distances, and track time with numbers that have a clear beginning and end. Infinity is different. It's not an extremely large number. It's an entirely different category of being, one that our brains, evolved to navigate a finite world, are spectacularly ill-equipped to visualize. We can manipulate infinity with the rigorous rules of mathematics, but when we try to apply it to the physical world, we run into paradoxes and conceptual walls that challenge the very notion of a sensible, predictable reality. Consider one of the most famous puzzles, Hilbert's Hotel, a thought experiment designed to reveal the bizarre logic of the infinite. Imagine a hotel with an infinite number of rooms, all of which are occupied by an infinite number of guests. One night, a new guest arrives looking for a room. In a finite hotel, they would be turned away. But in Hilbert's Hotel, the manager simply asks every current guest to move to the room number 1 higher than their own. The guest in room 1 moves to room 2, the guest in room 2 moves to room 3, and so on, all the way down the infinite corridor. This frees up room 1 for the new arrival. Astonishingly, even if an infinitely large coach pulls up with an infinite number of new guests, the manager can still accommodate them all by moving each current guest to the room number twice their own, freeing up all the infinitely many odd-numbered rooms. The hotel was full, yet it could always make more space. Now apply this to the multiverse. If there is an infinite number of bubble universes, and an infinite number of them are absolutely identical to our own, does adding or subtracting a few billion more universes change the total? Not at all. The total remains infinite. This reveals a strange property. You cannot meaningfully compare the sizes of different infinite sets in the same way you compare finite collections. An infinite multiverse containing our universe and one that does not could, in a mathematical sense, be considered the same size. This leads to a critical problem for physics, the measure problem. If the multiverse is truly infinite and contains every possible universe, then literally every event that has a non-zero probability of happening does happen, not just once, but an infinite number of times. This sounds definitive, but it creates a serious issue for making predictions. How do we calculate the probability of anything? In an infinite ensemble, there will be an infinite number of universes where you win the lottery every day of your life, and an infinite number where you are struck by lightning every time you step outside. So are all outcomes equally likely? Clearly not in our experience. The problem is that some infinities can be larger or denser than others. Imagine 2 sets of numbers, the set of all whole numbers and the set of all numbers between 2 and 3. Both are infinite, but if you pick a number at random from the entire number line, you are infinitely more likely to pick a number that is not between 2 and 3. The probability is essentially 0. Similarly, in the multiverse, the key question is not just if something happens, but how often it happens relative to everything else. We need a measure, a way to weigh the different infinite sets of universes against each other to determine what is common and what is rare. Without a solution to the measure problem, the predictive power of the multiverse concept remains frustratingly limited. It can explain everything in principle, but predict almost nothing in practice. These challenges have led some physicists and philosophers to question whether an actual physical infinity can truly exist. Our most successful physical theories, from general relativity to quantum mechanics, tend to break down when faced with the truly infinite, such as the singularities at the center of black holes or the beginning of the Big Bang. This suggests that infinity might be a useful mathematical idealization, but not a feature of the real world. Perhaps the universe is fundamentally discrete at the tiniest possible scale, the Planck scale. Just as a digital image is made of a finite number of pixels, space-time itself might be composed of tiny, indivisible units. If this is true, then the number of possible states in any region of space, and perhaps in the entire cosmos, is finite, albeit astronomically huge. This would mean that even in a vast multiverse, the total number of distinct universes could be a finite, albeit incomprehensibly large number. It wouldn't be an endless list, but a colossal yet countable collection. This perspective replaces the haunting, open-ended nature of infinity with a framework that is, in principle, more manageable and less paradoxical. This is where the mathematical universe hypothesis offers a potential path forward, providing a startlingly concrete answer to the question of how many. As we've discussed, this hypothesis proposes that every self-consistent mathematical structure has physical existence. Our universe isn't just described by math, it is a specific mathematical structure. The astonishing implication is that the multiverse becomes the set of all mathematical structures. This might seem like the ultimate leap into the abstract, but it actually provides a way to ground the multiverse in a precise, well-defined domain, the landscape of mathematics itself. Instead of asking the nebulous question, how many physical universes are there, we can ask the more rigorous question, how many mathematically consistent structures are there? The answer, as explored by mathematicians, is that there is not just one infinity, but an infinite hierarchy of them, each vastly larger than the last. The number of possible mathematical structures is likely an uncountably infinite set, a level of infinity so dense that it defies any attempt at a complete catalogue. So, does this resolve the issue? In one sense, it offers a kind of finality. The Level 4 multiverse is the ultimate, all-encompassing ensemble. It contains every possible bubble universe, every quantum branch, every simulated reality, and every cosmos governed by laws we cannot even imagine. It is the totality of all that is logically possible. However, it also pushes the problem to a new level. Now we must grapple with the existence of mathematical structures that are consistent but utterly incomprehensible to us, based on logical systems alien to our own. The challenge shifts from counting physical worlds to navigating the vast and perhaps equally paradoxical realms of mathematical existence. The quest to understand the multiverse, it seems, ultimately leads us back to the very foundation of logic, mathematics, and the deep, perhaps unanswerable, question of why this particular mathematical structure we call home feels so solid, so tangible, and so real. While these leading theories paint a grand and expansive picture of reality, some of the most revolutionary ideas in modern physics are questioning the very foundations upon which they're built. We've journeyed through the cosmic foam of inflation and the branching paths of the quantum world. But what if our understanding of space and time themselves is fundamentally flawed? A new generation of physicists is working on frameworks that don't just add to the multiverse catalog, but could potentially rewrite the rules of existence in a way that makes the concept of a multiverse either unnecessary or completely different from anything we've yet imagined. These aren't just minor tweaks, they are profound challenges to the established order, suggesting that the continuum of space-time is not smooth and fundamental, but rather emerges from something deeper, more discrete, and utterly strange. One of the most compelling of these new approaches is loop quantum gravity, or LQG. Think of it as a rival to string theory in the quest for a theory of quantum gravity, but with a completely different philosophy. String theory tries to unify all forces by proposing that particles are tiny, vibrating strings in a universe with extra dimensions. Loop quantum gravity, however, takes a more direct path. It asks a deceptively simple question: what happens if we apply the rules of quantum mechanics not to particles or forces, but to the fabric of space and time themselves? The answer it provides is breathtaking. In LQG, space isn't a smooth, continuous backdrop the way we intuitively experience it. Instead, it's woven from a fabric of tiny, finite loops incredibly small, one-dimensional threads of gravitational field. These loops are woven together into a network, a spinning, dynamic web often called a spin network. The places where these loops intersect, the nodes of the network, represent the tiniest possible volumes of space quantized into discrete packets. There is no such thing as a volume smaller than this plank-sized grain. Similarly, time is also quantized. It flows not as a smooth river, but in the tiniest, indivisible ticks of a fundamental cosmic clock. This single idea has a dramatic consequence for one of the most troubling concepts in cosmology, the Big Bang singularity. In Einstein's general relativity, the Big Bang is the point where all the equations break down, a moment of infinite density and temperature where the universe emerged from a state that physics cannot describe. But in loop quantum gravity, because space is quantized, it cannot be compressed into an infinitely dense point. There is a smallest possible size. This means that if you rewind the cosmic film, the universe doesn't collapse to a singularity. Instead, it reaches a maximum density and then bounces. This is the core of the loop quantum cosmology model, which suggests our universe wasn't born from a singularity, but from the rebound of a previous contracting cosmos. Our Big Bang was actually a big bounce. This immediately creates a cyclical model of the universe, but one that is radically different from the brane collision cycles we discussed earlier. Here, the cycle is intrinsic to the quantum nature of gravity itself. So, what does this mean for the multiverse? It suggests a sequential multiverse strung along the arrow of time, an endless series of cosmic eons, each one a new universe born from the death of the last. It's a multiverse of renewal, not of parallel coexistence, where each cycle potentially inherits some quantum imprint from its predecessor, creating a cosmic lineage stretching infinitely into the past and future. Another fascinating approach that also does away with the smooth continuum of space-time is called causal dynamical triangulations, or CDT. Imagine you're trying to build the very fabric of reality from scratch, but you only have a box of the simplest building blocks imaginable, tiny, four-dimensional geometric shapes called simplexes. In CDT, physicists do exactly that. They use powerful computers to simulate how space-time might be constructed by gluing together vast numbers of these tiny, triangular blocks of space-time. The key rule, the causal part of the name, is that the assembly must respect the flow of time. Cause must always come before effect in the network. When researchers run these simulations, starting with a random jumble of these blocks, something remarkable happens. Under the right conditions, the chaotic soup of geometric shapes doesn't remain a disordered mess. It spontaneously self-organizes. A smooth, four-dimensional universe emerges all on its own, complete with the three dimensions of space and one of time we're familiar with. In this view, the space-time we inhabit isn't fundamental. It's an emergent property, a large-scale average of the frenetic, churning, discrete geometry at the Planck scale. Much like the smooth surface of a pond is an average of the frantic motion of countless water molecules. The implications of CDT for the multiverse are still being explored, but they are profound. If our familiar four-dimensional space-time is just one phase that this geometric soup can settle into, what other phases are possible? The simulations show that by tweaking the parameters, you can get wildly different outcomes. You might get a universe that is all time and no extended space, a crumpled, dysfunctional mess, or perhaps even a universe with more than one time dimension. This suggests a landscape of possible space-time geometries, a different kind of multiverse where the very dimensionality of reality can change from one domain to another. It's a multiverse not just of different physical constants, but of different structural frameworks for existence itself. Furthermore, by providing a way to model the universe without an initial singularity, CDT, like LQG, offers a pathway to ask what came before the Big Bang, opening the door to a cyclical or eternally existing cosmos that needs no inflationary multiverse to explain its origin. Now, let's venture into one of the most radical and mind-bending ideas in all of physics, the holographic principle, which we touched on earlier. But now, let's consider it not just as a feature of black holes, but as a potential fundamental principle governing the entire universe. The core claim is this: all the information that describes our three-dimensional universe, including you and everything you see, can be fully encoded on a two-dimensional surface at its boundary. Our reality, with its rich depth and volume, is a holographic projection. This isn't just a metaphor. The mathematics suggests that a theory of gravity in a three-dimensional volume is completely equivalent to a quantum field theory without gravity operating on its two-dimensional boundary. This is a duality that turns conventional wisdom on its head. For the multiverse, this principle offers a dramatic simplification. If every universe is fundamentally a two-dimensional information structure, then the vast proliferation of three-dimensional worlds in the inflationary multiverse might be an illusion. The true multiverse would be a collection of these two-dimensional screens, each one storing the complete data for a single cosmic projection. The dizzying variety of bubble universes could be reduced to a vast library of two-dimensional datasets, a cosmic archive whose physics might be much simpler to comprehend than the complex, emergent phenomena within the projected worlds. Finally, we come to a perspective that seeks to cut the Gordian knot entirely: cosmological natural selection, proposed by physicist Lee Smolin. This theory, which dovetails with the black hole cosmology we explored, presents a truly Darwinian vision of cosmic evolution. The idea is that universes that produce many black holes produce many offspring, as each black hole can spawn a new universe through a bounce. Crucially, when a new universe is born, its fundamental constants could be slightly different from its parent due to random quantum effects, much like genetic mutations in biology. Over an immense number of generations, this process would naturally select for universes that are exceptionally efficient at producing black holes. So, why is our universe so good at making stars, galaxies, and planets? Because these are all necessary stepping stones to creating black holes. In this view, the apparent fine-tuning for life is a happy byproduct. We exist in a universe that is finely tuned for making black holes, and complex life is just one of the things that can happen along the way. This theory provides a powerful, non-anthropic explanation for fine-tuning, and remarkably, it makes testable predictions. It suggests that the parameters of our universe should be optimized for black hole production, meaning that if we could change any constant just a little, the number of black holes would decrease. This offers a way to potentially falsify the idea, grounding a grand cosmic narrative in the realm of empirical science. It presents a multiverse that is not a static landscape, but a dynamic, evolving tree of life, where universes live, die, and reproduce, with our own cosmos being one particularly fruitful branch in an infinite family tree. Yet, even as we build these grand architectures of parallel realities, we stumble upon the most enigmatic ingredient of all, the conscious mind itself. It's one thing to propose that reality endlessly branches or that infinite bubbles float in a cosmic foam, but it's quite another to ask where we, the observers, fit into this picture. This brings us to a deep and controversial frontier where the cold equations of physics meet the warm, mysterious phenomenon of consciousness. The pivotal question is this: does consciousness merely arise as a passive byproduct inside certain complex universes, or could it play an active, even fundamental, role in shaping the multiverse itself? This isn't just philosophical speculation. It cuts to the heart of how we interpret the bizarre rules of quantum mechanics, the very theory that gives us the many worlds interpretation in the first place. To understand this knotty problem, we need to revisit the quantum measurement problem that we touched on earlier. In the traditional Copenhagen interpretation, A quantum particle exists in a blurry superposition of possibilities until it is observed or measured, at which point its wave function collapses into a single, definite state. But this immediately raises a troubling question. What exactly counts as a measurement? Is it the interaction with a laboratory instrument? Is it the registration of data in a computer? Or does it require a conscious being to finally look at the result and become aware of it? This line of thinking, pushed to its extreme, suggests that consciousness itself is the ultimate catalyst that forces the fuzzy quantum world to snap into a concrete reality. This idea, known as the consciousness causes collapse interpretation, was favored by some of the founders of quantum theory, like John von Neumann and Eugene Wigner. In this view, the vast multiverse of parallel possibilities never actually comes into being. Instead, a single reality is selected at the moment of conscious observation, meaning the entire cosmos depends on minds to bring it into full existence. It's a profound, if unsettling, proposition that places sentient life at the very center of cosmic causality. Now, contrast this with the many worlds interpretation, which seems to offer a much cleaner, more physicalist solution. In many worlds, there is no mysterious collapse. The universe, treated as a single quantum object, simply evolves deterministically according to the Schrödinger equation. When a quantum event occurs, all possible outcomes are realized, but in different, non-communicating branches of the universal wave function. In this picture, consciousness doesn't cause anything to happen. It is simply a physical process, a pattern of information processing that occurs within a brain. When a branching event happens, the conscious mind itself splits, with one copy experiencing one outcome in one branch and another copy experiencing a different outcome in another branch. There is no special moment of collapse triggered by awareness. Consciousness just goes along for the ride, following the inexorable flow of the quantum wave function into a multitude of timelines. This perspective is far more palatable to most physicists because it removes any special role for the mind, treating it as just another part of the physical world. Yet, this clean division is not the end of the story. Even within the many worlds framework, a fascinating puzzle remains, often called the preferred basis problem. The theory tells us the universe branches, but it doesn't specify how it chooses the specific ways to split. What defines the set of possible outcomes that become actualized in separate worlds? This is where some researchers, like David Deutsch and Simon Saunders, have proposed that consciousness, or more precisely, the flow of information that constitutes a conscious point of view, might help define the branching structure of reality. In this more nuanced view, the branches aren't defined by an external God's eye view of the universe, but from the inside, by what different configurations can stably record and process information differently. A conscious observer is the ultimate information processing system, and the branching of their memory and perception might be what actually delineates one world from another. So, while consciousness doesn't cause the branching, the specific way that conscious beings record and respond to quantum events could be what determines the particular grain of the multiverse, the specific way the infinite tapestry is woven. This leads to an even more radical proposal, one that attempts to bridge the gap between the material and the mental. Integrated Information Theory, or EIT, developed by neuroscientist Giulio Tononi, offers a mathematical framework for consciousness. It proposes that consciousness is not about what a system does, but about how it is structured internally. Specifically, a system is conscious to the degree that it integrates information. That is, the whole system has more information than the sum of its parts. IIT provides a way to measure this, a number called phi, which represents the amount of integrated information. Now, some theorists have begun to explore what happens when you apply this logic not just to brains, but to the universe as a whole. Could the entire cosmos be considered a conscious system? And more pertinently for our discussion, could the process of quantum branching be understood in terms of information integration? Perhaps when a quantum system becomes entangled with its environment in a certain way, it reaches a point where the information can no longer be integrated as a single whole, forcing it to split into separate, independent complexes of information, each one a new branch with its own distinct conscious perspective. In this speculative but fascinating view, the multiverse isn't just a collection of worlds. It's a structure of separated conscious experiences, constantly differentiating as information integrates and then divides. The implications of these ideas are nothing short of staggering for our understanding of personal identity. If the many worlds interpretation is correct and consciousness splits, then the notion of a single, continuous you becomes deeply problematic. At this very moment, with every quantum event in your brain, countless versions of your conscious self are being spun off into parallel timelines. The you reading this sentence is just one thread in an infinite tapestry of selves. This forces us to ask, what makes this particular stream of experience yours? The only thing that ties your experience together is the continuity of memory along this specific branch. But the other versions have an equal claim to your past up until their point of divergence. This perspective can feel alienating, as if your identity is being diluted across infinity. Yet, it also offers a strange kind of solace. Every regret, every missed opportunity is being lived out by another version of you. Every tragedy has been averted in another world. Your consciousness isn't being destroyed, it's being multiplied, with each copy embarking on its own unique and valuable journey. The multiverse, in this light, becomes the ultimate guarantor of possibility, ensuring that no potential experience is ever truly lost. Of course, while physicists are busy with their equations and telescopes, the idea of the multiverse has exploded into our living rooms and movie theaters, shaping how millions of people imagine these mind-bending possibilities. It's fascinating to see how our collective imagination has raced ahead of the science, creating vivid, dramatic, and often deeply personal stories about what it might mean to meet another version of yourself or step into a world where history took a different turn. These fictional portrayals aren't just frivolous entertainment. They act as a kind of public laboratory, a safe space where we can play with the emotional and philosophical consequences of these theories long before the mathematics is settled. Think about one of the most iconic vehicles for this idea, the TARDIS from Doctor Who. For decades, the Doctor hasn't been hopping between parallel Earths in the way we often think of the multiverse. Instead, the show explores a different kind of plurality, the vast diversity of life, cultures, and timelines across a single universe. However, its core premise is deeply multiversal in spirit. The Doctor is a time traveler, and the show constantly grapples with the branching of history. One wrong step, one tiny interference, and you get an alternate timeline, a universe where the UK becomes a fascist state, or where the pyramids are landing pads for alien starships. This mirrors the quantum many worlds idea in a narrative way, showing how a single change in the past can ripple forward to create an entirely different present, a world that is both familiar and terrifyingly alien. It's a powerful way to explore the weight of our choices, suggesting that every decision we make might be spawning a new, valid reality somewhere in the cosmic tapestry. Then we have the Marvel Cinematic Universe, which has recently placed the concept of the multiverse front and center. Shows like Loki and movies like Spider-Man, No Way Home, and Doctor Strange in the Multiverse of Madness give us a very specific and thrilling model. Here, the multiverse is often depicted as a structured, almost bureaucratic system. The Time Variance Authority in Loki polices a sacred timeline, pruning branches that deviate from the predetermined path. This is a fascinating twist on the idea of a multiverse. It suggests that while infinite branches are possible, there is a preferred, correct timeline, and all the others are considered dangerous anomalies. This stands in stark contrast to the scientific view, where all branches in the many worlds interpretation are equally real. No one branch is more sacred than another. Marvel's version introduces a layer of cosmic order and conflict, giving us heroes and villains who can literally battle over the very structure of reality itself. It makes the abstract concept of quantum branching into a visceral, dramatic struggle. And who can forget the sheer joy of Spider-Man: No Way Home, where we saw 3 different Peter Parkers from separate cinematic universes come together. This portrayal leans into another popular multiverse trope, the idea of variance. Each Spider-Man is a product of his own unique set of experiences, his own tragedies and triumphs. They are the same person at their core, yet their different paths have shaped them into distinct individuals. This is a beautiful, human-scale exploration of what the many worlds interpretation might mean for personal identity. It suggests that the you in another universe isn't just a carbon copy with a different hat. They are a genuine individual whose life has been molded by a different sequence of events, carrying their own unique scars and wisdom. It makes the multiverse feel personal, a story about brothers from other realities rather than cold, abstract physics. Comic books, of course, are the original multiverse pioneers. DC Comics has been exploring the concept since the 1960s with its Crisis events, where characters discover that their reality is just one of many Earths in a vast multiverse. Each Earth has its own version of heroes and villains, some with subtle differences, others with radical alterations. There's an Earth where the heroes are villains, an Earth where Batman is a vampire, and an Earth where history stopped in the 1950s. This is a direct parallel to the inflationary bubble universe theory or the string theory landscape. Each of these comic book Earths is like a separate bubble with its own local laws, not of physics but of narrative. They explore the idea that in an infinite ensemble of worlds, every possible combination of traits and events must occur. The scientific landscape of 10 to the 500 universes finds its pop culture equivalent in the infinite Earths of the DC multiverse, a playground where every what-if scenario can be brought to life. What's truly remarkable is how these fictional explorations often focus on the aspects of the multiverse that science can't yet address, the emotional and ethical dimensions. A scientific theory can tell you that an infinite number of versions of you might exist, but it can't tell you how it would feel to meet one of them. Would there be a sense of kinship, rivalry, existential horror? Films like Everything Everywhere All at Once tackle this head-on, showing the psychological toll of being aware of all your other lives. The protagonist, Evelyn, becomes overwhelmed by the mediocrity and failures of her other selves, a poignant commentary on our own regrets and the paths not taken. This gets at a profound philosophical question. If every possibility is realized, does our life choices lose their significance? The film argues that they do not. In fact, in the face of infinite chaos, the love and connections we forge in this specific reality are what ultimately give our lives meaning. It's a powerful humanist response to a potentially dehumanizing concept. These stories also serve as a fantastic bridge, translating complex scientific ideas into relatable metaphors. When a character opens a portal to another dimension, we get a visual representation of what a wormhole or a brain collision might look like. When they talk about vibrational frequencies separating parallel worlds, as in the Superman comic story, Crisis on Infinite Earths, or the Flash television show, they are offering a simplified, intuitive handle on the idea of different quantum states or compactified dimensions. While a physicist might wince at the imprecise use of terminology, this kind of poetic licensing is incredibly valuable. It sparks curiosity. A teenager watching Doctor Strange might be inspired to look up the real-world theory of the holographic principle or the string theory landscape, starting a journey of discovery that begins with a dazzling special effect and ends with a textbook. However, it's also important to recognize where these fictional portrayals diverge dramatically from current scientific thought. Most sci-fi multiverses are navigable. Heroes build machines or use innate powers to hop from one reality to another at will. In almost all legitimate scientific models, this is considered effectively impossible. The inflationary bubble universes are forever separated by unimaginable stretches of eternally inflating space. The branches of the many worlds interpretation are decoherent, meaning there is no physical mechanism to cross between them. The barrier isn't one of technology, it's a fundamental law of causality. Furthermore, fiction often plays fast and loose with the rules of identity and memory. Characters who cross over typically retain their memories and sense of self, whereas a more rigorous interpretation might suggest that the moment you enter another quantum branch, you cease to be you in any continuous sense. You might merge with or be replaced by your local counterpart. These divergences aren't flaws, they are narrative necessities. They allow for stories about characters we care about, facing challenges we can understand, even if the science has to be bent a little to make the plot work. This vibrant landscape of multiversal fiction ultimately does more than just entertain us. It prepares our collective psyche for the possibilities that science may one day confirm. For centuries, our worldview was dominantly singular and linear: one universe, one history, one future. The concept of a multiverse shatters that perspective, and popular culture is our way of rehearsing for that paradigm shift. It allows us to confront the existential dread and the exhilarating freedom of a cosmos where everything that can happen does happen. By putting a human face on these abstract theories, by showing us the laughter and tears of our other selves, stories in film, television, and comics are helping to weave the multiverse not just into our scientific understanding, but into our very mythology, ensuring that when the next great cosmological discovery is made, we will already have a language both emotional and intellectual to it meaning. So after this grand tour through cosmic foam, quantum branches, and mathematical ensembles, you might be expecting a final, definitive number to appear on screen, the ultimate answer to our question. The truth, however, is far more nuanced and arguably more fascinating. Modern cosmology does not offer a single, universally agreed upon tally for the number of multiverses. Instead, we are presented with a spectrum of possibilities, each tied to a specific theoretical framework, and our best estimate depends entirely on which model you find most compelling and where the current weight of evidence seems to be leaning. If we were to survey the broader physics community today, the concept of an inflationary multiverse, born from eternal inflation, would likely garner the most widespread, albeit cautious, support. This isn't because we have direct proof of other bubbles, but because the theory of inflation itself has been so spectacularly successful at explaining the features of our own universe: its uniformity, its flatness, the pattern of galaxies we see. Since eternal inflation is a very natural, almost inevitable extension of many inflationary models, it carries a certain persuasive weight by association. In this view, the most honest answer to how many is a straightforward yet bewildering infinite. The process is ongoing and endless, creating a number of bubble universes that transcends any finite quantity. This infinite answer, however, comes with the heavy baggage of the measure problem we discussed, making it a powerful concept that is still grappling with its own philosophical and mathematical consequences. A strong contender, particularly among theorists working on unification, is the string theory landscape. Here, the estimate is not infinite in the same way, but it presents a number so vast it might as well be. The figure of 10 to the power of 500 possible vacuum states represents a different kind of plurality, a finite but incomprehensibly large portfolio of possible physical laws. When combined with eternal inflation, which would tirelessly churn out bubbles realizing all these possibilities, you get a multiverse that is infinite in number but finite in its variety of fundamental laws. This synthesis offers a potential pathway to explaining the fine-tuning of our universe without resorting to pure, unstructured infinity, and it's this promise that keeps the landscape a central focus of much theoretical research. When we step into the realm of quantum mechanics, the consensus fractures dramatically. The many worlds interpretation is taken seriously by a significant and respected portion of the physics community, seen by its proponents as the most elegant way to avoid the fuzzy, ad hoc concept of wave function collapse. Yet it remains deeply controversial. For every physicist who sees it as a straightforward reading of the equations, another sees it as an ontologically extravagant solution to a problem that might be resolved in other ways. If it is correct, the number of parallel worlds is again effectively infinite, but of a uniquely frantic and personal kind, branching with every quantum event. So, while it's a dominant player in the interpretation debate, it is far from a settled consensus, and its tally remains in the domain of spirited philosophical dispute. Looking at the more speculative frontiers, the Level 4 mathematical multiverse is perhaps the most all-encompassing vision, but it is also the one with the least direct connection to empirical testing. Its proponents argue for its logical inevitability, but many physicists remain skeptical, questioning whether such a grandiose concept can even be considered science. The brain multiverse and cyclic models are compelling ideas that emerge naturally from string theory and attempts to resolve the Big Bang singularity, but they currently lack the corroborating evidence that would elevate them to a mainstream consensus. They represent exciting and active research programs rather than established dogma. So why does this question remain so stubbornly open? The fundamental issue is one of empirical verification. The defining feature of most multiverse theories is that the other universes are, by their very nature, causally disconnected from our own. We cannot see them, touch them, or receive any signal from them. This places them in a precarious position from a strictly scientific standpoint. How do you prove something you can never observe? The scientific method thrives on testable predictions and falsifiable claims. For multiverse theories, the evidence is almost entirely circumstantial. We build a model like inflation that beautifully explains everything we can see in our cosmos, and that model then predicts the existence of other universes as a natural consequence. The evidence for the multiverse, in this view, is the overwhelming success of the theories that imply it. This has led to a fascinating and sometimes heated debate about the very definition of science. Critics argue that a theory that predicts a near-infinite number of unobservable universes is not science but metaphysics, an untestable and therefore unfalsifiable proposition. Supporters counter that we are not testing for the other universes directly, but for the underlying framework. Every time we measure a detail in the cosmic microwave background that matches inflationary predictions, or every time a particle accelerator confirms a prediction of the standard model, we are indirectly strengthening the case for the theories that naturally give rise to a multiverse. It's a chain of reasoning, not a direct observation. Therefore, the current scientific consensus is not a number, but a posture. It is a consensus that our best and most successful theories of fundamental physics, inflation, quantum mechanics, string theory, point insistently toward a reality far grander than our single observable universe. There is a widespread acknowledgement that the fine-tuning problem is real and demands an explanation, and that the multiverse provides a powerful, non-theistic solution. The prevailing mood is one of open-minded exploration. Physicists continue to search for those subtle fingerprints, anomalies in the CMB, specific signatures in primordial gravitational waves, or any other indirect clue that could tip the scales decisively toward one multiverse model or another. The ultimate tally remains one of the great unanswered questions, a mystery that drives us to refine our theories, question our assumptions, and look ever deeper into the strange and beautiful mathematical fabric of reality. We have journeyed together through a landscape of possibilities so vast it defies the very language we use to describe it. From the eternal, self-replicating foam of inflationary bubbles to the intimate, moment-by-moment branching of quantum realities, and onward to the ultimate mathematical ensemble where every consistent structure exists, we've explored the farthest frontiers of what physics can suggest about the nature of existence. We've stood at the edge of black holes and considered that they might be cosmic wombs, and we've peered into the holographic code that could be the source of our three-dimensional illusion. We've even confronted the possibility that our entire reality might be a simulation running on some unfathomable computer in a basement universe. It has been a tour of the utterly bizarre, the profoundly beautiful, and the philosophically dizzying. And after surveying this incredible cosmic catalogue, we are left with a question that is both simple and impossibly complex. So how many multiverses are there? The most honest answer is that we cannot give you a single, definitive number. The tally is not a fixed digit waiting to be discovered. Instead, it is a spectrum of answers, each one tied to a different vision of reality's fundamental architecture. Is it the straightforward, spatial infinity of an endless cosmos? Is it the frantic, exponential infinity of quantum branches? Or is it the finite but astronomically large portfolio of 10 to the 500 possibilities in the string theory landscape? The number you get depends entirely on which doorway you choose to walk through. This isn't a sign of scientific failure. It is a reflection of the breathtaking richness of the ideas themselves. We are at the very frontier of knowledge, where our most powerful theories point beyond the solitary universe we call home, but have not yet converged on a single, unified picture of what lies beyond. Yet, the true value of this exploration may not lie in finding a final answer, but in the journey itself. Asking these questions, following the math where it leads, even when it leads to places stranger than any fiction, reshapes our understanding of our own place in the grand scheme. It forces us to reconsider what is real, what is possible, and what it means to be a conscious observer in a cosmos that might be endlessly fertile. The sheer fact that our best scientific models naturally suggest a reality of such immense plurality is in itself one of the most profound discoveries of modern thought. It tells us that the universe is far more creative, far more extravagant, and far more mysterious than we ever dared to dream. This is not an end point, but an invitation. The quest to understand the fabric of reality is one of the great human adventures, and it is fueled by a simple, powerful engine, curiosity. Every strange theory, every wild possibility, every unanswered question is a testament to our innate drive to look up at the stars and wonder what else is out there. The universe, or perhaps we should say the multiverse, is not a puzzle to be solved and put away. It is a continuous, unfolding mystery, asking us to keep questioning, to keep exploring, and to remain forever open to the wonder of what might be. We would love to continue this cosmic conversation with you. Of all the mind-bending theories we discussed today, the inflationary bubbles, the many worlds branches, the mathematical ensembles, the simulated realities, or any other, which one captures your imagination the most? Let us know your favorite vision of the multiverse in the comments below. And if you enjoyed this journey to the edge of reality, be sure to subscribe and hit the notification bell. There are countless more cosmic mysteries waiting for